Okay, we're getting started. Please come in. Okay, it's still by university standards, it's still relatively. But guys, try to come on time, otherwise it gets complicated. Okay. How's it looking there, Nick? Are there people waiting there, or we can still wait a bit? So we'll still wait a bit for people, but I can use the extra time to give you something of information that the others are going to miss, which is we're going to have a second workshop reception. We don't normally do this, but we felt like we have to do a second one. So today, after Slav Petrov's talk, we will also have, like, let's say, a sunset party that will have more of a welcome reception feeling than yesterday. So that don't tell the other guys that they arrive late, right? They don't deserve it. They arrive late. So keep it between us. You just say we're going somewhere to the bathroom, and then we all do the party, and they miss it. And then let's wait a bit more, maybe 5 minutes more. Okay. No, él no trae nada de vino, nada de ser bebido. O onde está, realmente. Eu acho que foi uma empresa nova. Foi uma empresa nova que passou um pouco por isso, não sei. What do you think, Bhiksha? Like, you can wait 5 minutes?
Yeah, I can wait.
Uma coisa que está a acontecer no técnico do primeiro instituto, que é o cientismo individual.
Work from home. Ficam com a primeira ajuda. Work from home. Pô, está tudo a mudar muito.
Nos Estados Unidos também está a acontecer isso. Os colegas americanos que têm um estilo radical.
Okay, so Nick close the door for a few minutes. It is decided. It is decided. Okay, now. Okay, so, you see, they were waiting for the last minute. Come on, guys, don't come late. We just closed the door and then you came. You're like a cat. Okay, guys, so we're getting started with our first lecture. We have here the honor of having Bhiksha. He's a professor at CMU, where he also did his PhD. He did so much stuff and more stuff that he will do. That he worked at Industry, Compact, in also Mitsubishi Research Laboratories. Then as a professor at CMU, did a lot of stuff in the domain of speech, fundamentally. Now also neural networks. He pioneered like private speech processing. He also did the Sphinx. There was many speech toolkits, right? And one of the best known were Sphinx for a long while. So he also did that. So much research, so many smart people work with him, and also now are old. We're all old, right? So we're really honored to have him here. And yeah, very, very happy to just hear his lecture. So.
May I? So thank you, everybody. And thank you, Ramon, for the introduction. I have a request for all of you guys. I would like to request, can you hear me? Okay. I'd like to request all of you to shut your laptops. I've come halfway around the world. I'm tired. I have a neurological problem. It's hard for me to walk. After about 15 minutes, I will have trouble breathing. There's nothing more demotivating when I have my situation than to see all of you with your laptop staring into a different world. If you must open your laptop, I have nothing against it. Please leave the room because it's kind to me, right? So please shut your laptops. And then I always have this request, no matter where I give my lecture. Okay. So let me begin. This is just a 3-hour tutorial. I'm not going to be teaching you anything profound. It's my philosophy in life that profundity is best meant for papers. What I can do over here is to show you a bunch of pretty pictures and hope that gives you some kind of insight into some of the things that we learn. And so we're going to learn about what a neural network is, some historical perspective, what these things can model, and what they actually learn. If you never saw this lecture, it wouldn't change your life. So this is me, but I only do that when crimes happen and somebody calls the secret code. Otherwise, I look like this. I'm a professor in the Language Technologies Institute in Carnegie Mellon University. I have additional affiliations in the machine learning department, the electrical and computer engineering department, and music tech. I am also a visiting professor at the Mohammed bin Zayed University of AI in the United Arab Emirates. If you have any questions, if you would just like to collaborate with me, if you're just curious as to who I am, my email is up there. So the lecture is in a few parts, and I've been trimming my slides. So at this point, I'll be honest, I no longer remember how many parts the lecture has. I think it's 3. So nothing new. The reason we're all here is we are trying to learn about neural networks. They're taking over the world. They've become basically the only way of doing AI and machine learning anymore. And the kind of state of the art they have established in most problems is something that you cannot even hope to achieve with older classical techniques. So how did this happen? It turns out that not very long ago, if you just went back 9 years, 2015 or even early 2016, nobody was using neural networks. It was, there were people working on it, but mostly, it was a curiosity because we hadn't managed to get it to really work. And then something dramatic happened in 2016. Many dramatic things happened. One of the first, this was Microsoft's AI beats humans at speech recognition. Notice the date, October 20, 2016. And so suddenly, for the first time, we had been working on speech recognition, I one of the many, for over 50 years. And if you use Siri, if you used any recognition system, what came out was generally more a party joke than serious stuff. And then suddenly, for the first time in October 2016, Microsoft came up with a recognizer that outperformed human beings on a task. And now, of course, today, your automatic speech recognizer recognizes speech better than you do. And that's shocking, right? And this was simply because of neural networks. Or this one. This is found in translation, more accurate, fluent sentences in Google Translate. This is also, I think, November 2016. So just before that, in October 2016, if you had translated, Google Translate was the best translator around, even then. But if you translated English to Spanish and then translated that Spanish back to English, what came back was mostly a party joke. It didn't work. And then one fine day in late 2016, suddenly you had machine translation systems that were so good that the professionals were using it as their first cut. And now, of course, the systems are phenomenally good. What happened? We kicked in neural networks. Or object segmentation and images and labeling, something of this kind. So this is still from 2016. And this was impossible just the year prior. And this was also made feasible by neural networks. Or games. For the longest time, we thought that the limit of intelligence, of a measure of intelligence, was to play intelligent games like chess, like Go, because this is, these are not, these are very complicated games based on strategy. If you think of chess, the number of possible states is 10 raised to 120. If you think of Go, the number of possible states is 10 raised to 128 or 100 and some, whatever. It's an absurdly large number. And so it was thought that you needed human intelligence to figure this out. Now, we managed to beat chess in 1995, but Go seemed like the ultimate frontier. And then suddenly in 2016, again, see the magic date, right? We came up with AlphaGo, which could learn to play Go and beat the world champion. And these days, these games can actually start from scratch and learn how to play in a few hours and beat every human being existing. And that's because of neural networks. and so on. The first time we actually managed to get captions of this kind for images also in 2016. So there was this phase transition in 2016 where lots of amazing things happened. And 9 years later, here we are. Pretty much everything is neural networks here. We have large language models which have taken over the world. Something like Sora can create movies. In fact, there was a video which came out only 2 days ago where some kid in China created an entire music video where the song, the background music, and the visuals, which are very fancy, and the characters and the visuals are all created by AI. And it's very plausible. So maybe in just a few years' time, you won't need bands. The AI will take care of everything. So all of this, and a whole lot more, right? Biochemistry, medicine, public health, self-driving cars, speech processing, even predicting stock markets. Everything is using neural networks these days. So the question naturally is, what are these things? What are these neural networks, right? And of course, if you don't know neural networks, you're not going to get a job anymore, especially in the tech world. So what are these neural networks? In each case, it's this crazy black box which takes an input and produces some kind of an output. So it could take in a voice signal, generate a transcription, take in an image, generate a caption, take in a game state, give you the next move. There's something magic happening in the middle. What's that magic? We don't know. But then what we observe is that every one of these tasks is a fundamentally human task. You don't see rocks and chimpanzees play chess. Capturing images, playing games, all of these are human tasks powered by the human brain. So to understand how these things can be done, maybe we want to begin studying the human brain. Or even before that, this business of cognition. What does it mean to have cognition? Now, people have been curious about human ability of cognition for thousands of years. Humans can do a whole lot of things. We can learn, we can solve problems, we can recognize patterns, we can create. You can just be standing in the shower, doing absolutely nothing, having a shower, and you get some crazy ideas of a snake gobbling its own tail, and then you come up with an invention, right? Why does this happen? We'd like to know why, we'd like to know how, so that we can emulate it. And so, of course, that's what we will try. But then here's the problem. If the brain was simple enough to be understood, we would be too simple to understand it. This is Marvin Minsky, and it's very true. And that doesn't stop us from trying. And so the earliest models of cognition go back to 400 BC at least. This was the earliest hypotheses were by Plato and Aristotle. This one is, I think some of you must have seen this painting. This is in the Sistine Chapel, the School of Athens. And it shows all the famous philosophers and scientists through history, right until the 15th century. And right in the middle are Plato and Aristotle. Anyway, Plato came up with this idea that the brain works through associations. What do we mean by associations? Anytime you experience two percepts together, you form an association. So you see lightning, and slightly later you hear thunder. So you begin associating lightning with thunder. And then thereafter, if you see lightning, you're going to expect thunder. If you hear thunder, you're going to say, I think lightning struck someplace. So you form this association. And it turns out that this business of saying that we associate percepts to come up with reasoning and inferences is actually a brilliant idea. We still do it. We just put symbols to it. We call it math. But at the end of the day, all of our models are based on associationism. And so, of course, this kind of ruled the roost. But then it doesn't answer the basic question. Sure, we are forming associations, but how does the brain work? Where are these associations stored? And this question persisted till about the mid-1800s, by which time microscopy had become so good that we knew exactly how the brain was constructed. We know that the brain is a large, messy network of cells, which we call neurons. And each neuron connects out to many neurons, and many neurons connect into each neuron. And somehow, this holds all of our ideas. So the first person to come up with a theory of how this worked was this guy, Alexander Bain. He was a philosopher, mathematician, linguist, back in the day. Scientists were polymaths, all of them. And so in 1873, he came up with the first theory, which is the modern neural network. He said, the magic lies not in the units. The units themselves are very simple. It lies in how they are connected to one another. And he even came up with some example models of this kind, where he showed, for example, that in this picture, if you assume that each neuron activates, it fires, if it gets at least 2 inputs, then depending on the pattern of inputs, X, Y, or Z could all fire. The same network, different inputs result in different output patterns. Now, this seems so obvious to us, but back in 1873, this seemed like an absurdity, and people mocked him. And there was a lot of pushback against this idea. He also came up with this examples where simply changing the intensity of the input could change the output pattern. So here, for example, Y gets 3 copies of the input, X gets 2 copies. So if you have a low intensity signal, Y will fire, a high intensity signal will make both of them fire. Again, this seems obvious to us. It wasn't in those days, and there was a lot of pushback. And he even came up with an idea of how the brain actually learns these patterns and how to form these connections. He said when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. It's a lot of complicated words, but basically he came up with Hebbian learning. And this was in 1873. So if you've ever wondered how old neural networks are, the modern neural network, along with all of the learning algorithms, dates back 150 years. So what happened between 150 years ago and 2016? A lot, but mostly nothing. And it has to starts with this. Bain said he thought about it because there was so much pushback. And eventually he began doubting himself. In 1875, he said that there must be 1 million neurons and about 5 billion connections between them so that you can store 20,000 percepts. But then quickly realized that 20,000 doesn't even begin to cover the world. And then you have to store partially learned percepts. And so by the time you get to it, he figured that all those people criticizing him were right. There just wasn't enough brain to hold all of this. So he apologized, said I'm wrong, and died. Unfortunately, right? He was right. The reality is that the typical brain has 80 billion neurons, and it has about 100 trillion connections. There is more than enough matter in your head to do everything Bain suggested and much, much more. And this is even in the smallest of the human brains. We have very powerful computes. And so this is how the modern world thinks we work. We are connectionist machines. Our human brain is a connectionist machine. Neurons connect to other neurons, and the processing capacity of our brain is a function of these connections. And so your modern connectionist machines, your neural networks, emulate the brain in the structure. And so what is a connectionist machine? It's basically a network of very simple processing elements. And all world knowledge is stored not in the elements, but in the manner in which these elements are connected to one another. Now, this is fundamentally different from your cell phone or the computers that you work on. All of these, as you all know, have the so-called von Neumann architecture, or the Harvard architecture, where this is a processor and there's a separate memory. And the programs and data are stored in the memory. And so you can make the same device do many different things simply by changing what's in memory. Now, this is great. It's very flexible. And this is why we're able to come. We are in the state of computational sophistication that we are in today. But connectionist machines, which seem to be more powerful in terms of what they can do, have a fundamental problem that the computer is the program. The manner in which you connected things is the program. So if you want to change what the program computer does, you change the entire computer. You have to redo it, which is why we don't actually go off and build connectionist machines. We emulate them on von Neumann architectures. Anyway, having established this, so here's the story that we've seen so far. Neural network-based AI has taken over most AI tasks. They originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism. And the most recent model of the brain is connectionist. Neurons connect to neurons, and the workings of the brain are encoded in these connections. And current neural networks emulate the structure. They are connectionist machines. So moving on, here's what we have. We have our neural networks are connectionist machines. These are networks of very simple processing elements. All world knowledge is stored in the connections between the elements. But then, what are these basic elements? Now, to understand what these basic elements are, we are going to go back to where we began. We are going to look at the human brain. And the basic elements in the human brain are nerves. Now, here's what a nerve looks like. The neuron in the brain looks like. It's got a head with lots of little fibers called dendrites through which incoming signals arrive. When the cumulative incoming signal exceeds some threshold, I mean, at a high level, you can think of it this way. The neuron fires, and that signal goes up this long leg called the axon to other neurons. And this axon is protected by something called the myelin sheath, which is mostly fat, glial cells. And here's something I like to tell everybody. How intelligent you are depends on how much fat you have in your head, not how many neurons you have in your head. So being called a fat head is a major compliment, right? And this is true. They've actually studied Einstein's brain, and they didn't find more neurons than other people. What they found was a lot more fat. So because it protects your cells. Anyway, now, so this is how the neuron works. Now we need a computational model for this. And the first guys to come up with this were these two guys. One of them is McCullough and Pitts. And we owe everything that we do with neural networks today to these two guys. Warren McCullough was a professor in the University of Chicago. And Walter Pitts was a homeless guy who ended up at his door one day. Now I'll let you figure out who's the professor and who's the homeless guy, right? The guy to the left with the wine glass is the professor, and the guy in the tie is Walter Pitts. Okay, he was only 20 years old, and he hadn't even gone to college. He'd basically been through high school. He used to correspond with Bertrand Russell. He ran away from home and ended up in the University of Chicago and came up with this amazing paper called A Logical Calculus of the Ideas Immanent in Nervous Activity back in 1943, the basis of everything we do, where he came up with a mathematical model for the neuron, which explained it as a Boolean entity. So how does this work? They said that any neuron has two kinds of connections. Connections through which when signals come in, the neuron is triggered to fire. And connections where if any signal comes up that connection, the neuron is not going to fire regardless of what else happens. So these are the excitatory and inhibitory connections. And using this, they showed that you can actually emulate pretty much any Boolean gate. So here, if you assume the little triangles are the neurons, a neuron will fire if it gets two inputs. The first signal, top left, if the first neuron 1 fires, after a little bit, neuron 2 is going to get two inputs, it will fire. So it's just a delay. The second one, if either neuron 1 or neuron 2 fire, then neuron 3 is going to get two inputs. And so it's A or B, or 1 or 2, right? Yeah, okay. All right. So, and then similarly, you can see the one to the bottom left. Anybody tell me what that Boolean gate is? The one to the bottom left? That's an AND, right? You need both 1 and 2 to fire for the third one to get two inputs. And then the fourth one, it's using both excitatory and inhibitory connections. It's 1 and not 2. If 1 fires and 2 doesn't fire, that's when 3 is going to fire. So you can see that you can build very complicated Boolean circuits with it. And so McCullough and Pitts actually showed how you can model pretty much any Boolean function with it. They even showed that if you attach a tape to it, it's basically a Turing machine. But they didn't give us a learning mechanism. They just gave us some kind of a complicated architecture, and we needed more than this. And for that, we had to wait several years. The first attempt at trying to explain how these things would learn was by this guy, Donald Hebb, where he came up with this famous theory, which was succinctly stated as neurons that fire together, wire together, right? So folks, may I request that you shut your laptops? For those of you who came in late, this is my standard request to everybody. please shut your laptops. And if you do want to keep work on your laptops, please leave the room. I'll wait for a bit for you to shut your laptops. Thank you. Right. Now, so here's how Hebbian learning works. A neuron, the way neurons connect to one another, they don't actually touch one another. Instead, there's a synaptic knob. And anytime one neuron fires, it emits some chemicals through this knob, which excites the next neuron. And there's a biological property. Anytime a neuron fires, and this causes the second neuron to fire, the synaptic knob gets a little larger, which means the next time it can release more chemicals. So if you can think of it in mathematical terms, if there's a weight for the connection between the neurons, anytime the neuron X causes neuron Y to fire, the weight increases. So if X and Y are Boolean, the weight increases if both X and Y take the value 1. So the learning rule is W equals W plus eta times XY. The weight increases when both X and Y fire, if X causes Y to fire. And this is a beautiful learning rule. We still use it everywhere. But in this, stated in this manner, there's one fatal flaw. And I'm sure most of you have already observed this fatal flaw. There's no way for the weight to decrease. So it will keep increasing and eventually saturate. And at some point, the whole system is going to become useless. And so we need some more modification for this. And that waited till the 50s by this guy, Frank Rosenblatt, who was a psychologist and logician and who invented basically everything, also known as the perceptron in 1958. He got a lot of money from the Navy for it. And his basic model was fairly complicated, but it consisted of simple units of this kind, where he said that the neuron has many inputs. Each input has a corresponding weight. And so the neuron is going to get a weighted sum of all of its inputs. If the weighted sum exceeds some threshold, the neuron will fire, otherwise it will not, which goes back to a model of the neuron, biological neuron that we saw earlier. And so although his original model was a complicated structure with thousands of such units, the basic unit itself was just this guy, where it saw a weighted sum and fired if the weighted sum exceeded some threshold. Now, unfortunately, due to some various confusions, eventually the world came to recognize the picture to the right as Rosenblatt's model and not the picture to the left. Now, even so, there was a lot of hype. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of existence. 1958, Frankenstein monster designed by the Navy that thinks, 1958, right? So there was so much hype that when this hype didn't come to fruition, the funding for neural network research died. So if you're ever wondering why we waited till 2016, it's because at every point, people either doubted themselves or there was overstating. And so research slowed down. But then Rosenblatt also came up with this learning rule, which said this looks a lot like the Hebbian learning rule. But when you're looking at the Hebbian learning rule, there is no notion of a supervision. You say two neurons begin to connect to each other more strongly if both of them fire together. But there's no notion of, do you really want this to happen? So there's no supervision. Now, Rosenblatt was the first to introduce the notion of supervision. This was his magic, his contribution to science. He said the neuron has a desired output. There are conditions under which it must fire and other conditions under which it must not. And the only time the weight changes is when the desired output differs from the actual output of the neuron, which makes a lot of sense. Now, and this was great, but this applies still to the basic neuron that we saw over here. And the basic neuron is very powerful. Again, it's seeing a weighted combination of inputs and it's firing. So here I have the threshold shown inside the circle, the weights shown above the lines. And as you can see, the figure to the top left receives a total input of 2 if both X and Y are 1, which matches the threshold, and it will fire. So it only fires when both X and Y are 1, so it's X and Y. The one to the right, the threshold is 0. If X is 1, the weight is -1, the weights can be negative. If X is 1, then the total input coming in is negative, it will not fire. If X is 0, the total input is coming in as 0, which matches the threshold and it will fire. So it's a NOT gate. The one at the bottom, that's an OR, as you can see. If either X or Y fire, it's going to fire. So you can emulate pretty much any Boolean gate using this unit. But unfortunately, as people discovered, it's not universal. It cannot even do a simple XOR. There's no way of assigning weights where you can compute an XOR of two inputs. And so back to the drawing board, right? Here's this very powerful unit. We'll see more of this in a few minutes. But it's not even able to compute something simple as an XOR. How do we get past that? We go back to the brain. The brain is not a single neuron. The brain is a network of neurons. And so what we want to do is to begin networking these guys. And then once you begin networking these guys, you see it can do pretty much anything. So here, the neuron on top does X or Y. The one below says not X or not Y. And the final one ANDs the two. And now you get an XOR gate. Now, this is where we can introduce some terminology. We don't really care what the outputs of the neurons in the first level are. So we call them hidden neurons. And the one at the output, that's the output neuron. Its output is what we're interested in. But again, the principle is that although the units are simple and they have limitations, once we begin connecting them up, you can compute difficult Boolean functions. And once you realize that, you realize you can use these things to compute pretty much any Boolean function. So here's a very ugly Boolean function of 4 inputs. I can just create a bunch of network of a bunch of neurons and it will compute it. So perceptrons by themselves are pretty powerful, but not good enough. But once you connect them up into networked perceptrons, what we call multi-layer perceptrons, they can compute pretty much any Boolean function. So to add to our story, the neural network models are connectionist machines. They comprise networks of neural units. The McCullough and Pitts model models neurons as Boolean threshold gates. And it models the brain as performing propositional logic. So this was their contribution. Hebb's learning rule was an unsupervised learning rule, which said neurons that fire together, wire together. It's unstable and it has no supervision. And then Rosenblatt's perceptron, which was a variant of the original perceptron, but with a learning rule, actually added the notion of supervision and a desired signal and came up with a learning rule. And multi-layer perceptrons, which are networks of such perceptrons, can model arbitrarily complex Boolean functions. But then I'm talking about Boolean. My brain is not Boolean, nor is yours. We work on real valued inputs. We make real valued predictions, right? Even if I'm assuming Boolean predictions, we're working on real valued inputs, right? So then how can we square these? We can go back to the basic threshold unit. But now my inputs X are all real valued. The network is seeing a weighted sum of these real valued inputs. If the network weighted sum exceeds a threshold, it's going to fire. So if you think about it, there's also there's one way of thinking about it, that there's a two-stage compute. First, that I compute a weighted sum of the inputs. And the second, I pass this weighted sum through an activation function, which is a threshold function, which fires if this weighted sum exceeds the threshold. Your outputs are 1, otherwise it outputs a 0. And then once I separate the two, I can actually make the activation function somewhat different. Instead of being a threshold function, it can be something smoother, like a sigmoid, at which point you can think of it as outputting the probability of firing. Again, we will see this in a bit, right? So how does this unit behave? The neuron fires if the weighted sum exceeds a threshold. So the boundary between when it fires and when it doesn't fire is when the weighted sum is exactly equal to a threshold. Now, equating a weighted sum to a threshold is the equation for a hyperplane. So there is a hyperplane, and when the input is on one side of the hyperplane, the neuron fires. On the other side, it doesn't fire. And this is just a simple neuron. But then once you can observe this, you can see why this operates as any kind of Boolean gate. Now, if you had Boolean inputs, the inputs are all going to be either 0 or 1. So if I had 2 inputs, then the inputs are going to be either 0, 0, 1, 0, 0, 1, or 1, 1. And if my perceptron has a boundary between the 0 region and the 1 region shown in the top left figure, then it's going to fire when any of the inputs are 1. So that's an OR gate, right? On the other hand, if I move the boundary beyond the diagonal, it only fires when both inputs are 1. So this is an AND gate. And if I change the boundary to what I have on the right, it basically flips the Y and ignores the X. This is a NOT gate, right? So you can see how this linear classifier can actually compute Boolean functions. And now you can do something, see even something even more interesting, how you can compute complicated decision boundaries of this kind. I want a network. I want a function which will output a 1 if the input is within the pentagon and a 0 outside. So how can I do this? I can have one perceptron which outputs a 0 if the input is above that horizontal line. Another perceptron which outputs a 1 if it's to the left and 0 otherwise. A third for this boundary, a fourth for this boundary, a fifth for this boundary, and then a final perceptron which simply ANDs all 5, and voila, I have a pentagonal decision boundary, right? Now, once I can do this, I can do more crazy boundaries, like this one, this double pentagon. So here now I can have one subnetwork which models the first pentagon, the second one which models the second pentagon, or the two. It's still a multi-layer perceptron, right? But now I have a decision boundary which is a double pentagon. If I can do this, I can do something more crazy, like decision boundaries of this kind, like this funky figure to the left, or something that looks like a human or even a horse. All I need to do is to divvy it up into little polytopes, have a subnet for each of the polytopes, and OR them up, right? So you can see how this thing works. It can model pretty much what we have seen is that same thing. That was in 2 dimensions. I can make it in any number of dimensions. For example, if I'm trying to build a classifier for the digit 2, then there's some parameter, some feature space where the 2's lie within some region. And all I need to do is to build a network which captures the boundaries of that region. We saw exactly how you can do it. And so, what we have seen is that first, MLPs are connectionist computational models, which basically has layers of perceptrons. They can model pretty much any Boolean function. They are universal Boolean functions. You give me a Boolean function, I can construct an MLP for it. They can model pretty much any decision boundary. You give me a decision boundary, I can construct an MLP for it, which approximates it to arbitrary precision. And that's only Boolean functions and classifiers. What about real valued functions? We'll get to that. But even before that, is there a semantic interpretation to what's going on? I'm just looking at giving this from the perspective of, here are numbers, let's look at boundaries. But then about how when you perform perception, when you perceive things, you're not operating on numbers, you're actually operating on inferences, you're looking for patterns. So can I look for something similar with these networks as well? Now again, go back and look at this single perceptron. It's looking at a weighted sum of inputs and firing if this weighted sum exceeds the threshold, right? Now, what is the weighted sum of inputs? If I put all of the weights in a vector and all the inputs in a vector, the weighted sum is simply the inner product between the two vectors. So when is the inner product between two vectors maximum? When the two vectors are pointing in exactly the same direction. And so when I say that this inner product must exceed a threshold, it means that I'm allowing my x to deviate from my weight vector by a small angle. And so long as everything lies within that angle of the weight vector, it's going to fire. So in other words, my weight vector is a template, and I'm matching the input to this template. That's all I'm really doing. So once I learn this, it's very easy for me to even begin handcrafting perceptrons. For example, if I want to build a perceptron to recognize the digit 2 in an LED display, then my weights are simply going to look like the digit 2. And now anytime I get an input, I can compute the inner product between these two, which is basically the correlation. And if that exceeds a threshold, then I will fire, otherwise I will not, right? It's very simple. So you're actually looking for patterns. Your weights tell you what you're looking for. And what happens when you have a multi-layer perceptron? It's harder to make this kind of intuitions when these things get stacked deep, but it's not impossible, right? So when I have a multi-layer perceptron, I would say that, for example, I have a problem where I have these LED grids and I must figure out if the grid is showing a digit or not, then I know that digits are composed of certain kinds of patterns. So the first layer neurons, which are the most important, are going to be looking for the basic patterns that compose digits or patterns that make sure that confirm that the input is definitely not a digit. And then this next subsequent layers are simply going to be looking for patterns over these things. So for example, over here, you might find that the first neuron is looking for a combination of these input patterns that forms the digit 2. The second one looks for the digit 3. And the final output fires if any of the digits are found and otherwise not. So you're basically composing things on the, piecewise. But the key point is that the weights that you're looking at really tell you what patterns you're looking for. They are templates. That's something that we will use also. And so you can think of the network as a cascade of feature detectors. Higher level neurons compose complex templates from the features represented by the lower level neurons. And so to add to the lesson we've seen so far, when I'm using an MLP for classification, the network fires if the combination of detected basic features matches an acceptable pattern for the desired class of signal and not otherwise. So, if you were doing face detection, you're probably looking for appropriate combinations of noses, eyes, eyebrows, cheeks, and chin. And you would expect that the different layers of the network are learning to detect all of these features. Now, that's for Boolean functions and classification. But what about regression? We know multi-layer perceptrons can also compute real valued outputs. How would it do that? So I'll start with a very simple example. I have one neuron, which I have 2 neurons, and I have a single input, X. Neuron 1 fires if the input exceeds T1. Neuron 2 fires if the input exceeds T2. And then their outputs are summed with weights 1 and -1. Now, what happens? Assuming T1 is smaller than T2, as the input value keeps increasing, when the input is below T1, neither of them fires. When the input is between T1 and T2, the first neuron fires, but the second doesn't. So now the output is going to become a 1. When the input exceeds T2, both of them fire, they cancel each other out, the output becomes a 0. So now you have this little network which produces a 1 between T1 and T2 and 0 elsewhere. But then now, if I have a complicated, ugly function like this blue curve, I can compose it to arbitrary precision in my approximation simply by slicing out my domain into little regions and having one subnet for each of these regions. And I can add them up. So what this tells me is that my MLP can compose, and this idea generalizes to multiple dimensions too, although I've shown it only for a single scalar, right? So what this tells me is that MLPs can also model continuous valued functions. And when you're modeling continuous valued functions, this is why we call them universal approximators. As you can see from my example, it doesn't necessarily exactly get the function that you want, but it can compute an approximation to the function that's as precise as you want. You give me an error bound, and I can compose a model that gives you an error less than that bound. And so MLPs are universal approximators for pretty much any kind of function. Questions, anyone? No? Okay. So, all right, again, guys, may I request you to shut your laptops, please? This is the, do you mind shutting the laptop? Yeah. Thank you, right? Everybody has. All right, so let's continue. We see that these are universal approximators, but then what are the limitations? So here I'm going to be using my threshold activation perceptron, but again, I want you to remember that it doesn't have to be so, right? I can be putting any kind of other function to operate on the weighted sum of inputs. And so instead of just having a binary 0, 1 output, it could have a continuous valued output. Or you could have activations which are like tan H, the rectified linear unit, and what have you, right? But for now, I'm going to continue assuming a threshold activation because it makes explanations and intuitions very, very simple. So here's what an MLP is. It's basically a network of perceptrons, generally layered. But the moment I say this, we need some definitions. What does it mean? What does it mean for neurons to form a layer? How do we define a layer? We're speaking of deep neural networks. How do we define deep, right? Where do these definitions come from? Everything is formally defined. So first, what is a deep network and what's a layer? For that, we have to go back to graphs. Now, most, or at least some of you have studied graphs and graph theory. You know what it means for a graph, what the depth of a graph means. Now, assume you have a directed graph. A directed graph has one or more sources and one or more sinks. And all paths go from sources to sinks. And there's when you trace the paths from the source to the sink, then there's a longest path. Here, for example, this is a source, this is a sink. The longest path is 2. The depth of the graph is the length of the longest path from the source to the sink. Here, for example, I have a path of length 1, a path of length 2, and a path of length 3, but this graph has depth 3. So there's a notion of a depth of a graph, which is the length of the longest path from source to sink. So when I have a neural network, first, what does it mean for neurons to form a layer? Here, when I have a network of this kind, I can compute the depth with respect to the input, assuming the input to be the source. And here you can see that all of the red neurons are at a depth of 1 with respect to the input. So all the neurons which are at a depth of 1 with respect to the input form the first layer. These guys, the green neurons, although they're awkwardly placed, they all have a depth of 2 with respect to the input. So the green neurons form the second layer. The yellow neurons all have a depth of 3 with respect to the input. So the yellow neurons form the third layer, and the blue neurons form the fourth layer. So it's not about how it looks. There's really a formal definition for what a layer is. And there's also a formal definition for the depth of a network, which is going to be the distance, the longest distance from the input to the output. And a deep network is one where this distance is greater than 2. So here, for example, this distance is 3. And so this is a depth 3 network. And so it's a deep network. This one, the distance is only 2. So it's not a deep network. This one, although there are various paths from input to output of lengths 2, 3, 4, and 5, the greatest path is longest path is length 5. So it's a depth 5 network. It's a deep network. So long as the depth is greater than 2, it's called a deep network. Now, we've already seen that multi-layer perceptrons are basically layered connection networks of perceptrons. And the inputs can be real or Boolean. The outputs can be real or Boolean. They can have, and you can be computing a single value or a vector of outputs. But what can it compute? And meaning what kinds of input-output relationships can it model? And how does that relate to depth? So we will take a look at that. Now, we know that MLPs can approximate anything. They can approximate any Boolean function. They can approximate any, they can compute any Boolean function. Forget about approximate, right? They can approximate any classification boundary. They can approximate any continuous valued function. But then, what are the restrictions? So let's go back and consider the simplest case, Boolean functions. How well do MLPs model Boolean functions? We've already seen that an MLP can model any kind of Boolean gate, an AND gate, top left, a NOT gate, top right, an OR gate, bottom right. But then perceptrons, so not MLPs, but perceptrons can model any gate. But then perceptrons are remarkably powerful things. They can do a whole lot more than just Boolean gates. And this is why for the longest time, people actually thought that a single perceptron was a universal Boolean function. It was not. But here is something it can do. Here's a perceptron which fires if the total input is L. Now, the first L inputs have a weight of 1. The subsequent inputs have a weight of -1. So the only time that the total input is going to be L is if the first L inputs are all 1 and the subsequent inputs are all 0. If any of the lower inputs becomes 1, they're going to contribute a -1 to the sum. And so the total sum is going to be less than L. If any of the first L inputs are 0, then too, the total sum is going to be less than L. So the only condition under which this particular perceptron will fire is if the first L inputs are all 1 and the subsequent inputs are all 0. So you have this complicated function and of all of these x's and not of all of these remaining x's. So fairly complex, right? Or here is something else that you can do. This perceptron will fire if any of the first L inputs is 1 or if any of the subsequent inputs is 0. So this is like a negation of what we saw earlier, but then it's actually a fairly complicated function, right? And a single perceptron can take care of this. Not so fancy. This is still a Boolean gate, but here's something even more impressive. This perceptron is a majority gate. It will fire if at least k of the inputs are 1. So all of them have weight 1. And if at least k of the inputs are 1, this will fire. Now, it turns out that if you want to compose this using Boolean gates, that circuit is going to be exponentially large in the number of inputs. But you can do this with a single perceptron. So perceptrons are incredibly powerful, far, far more powerful than Boolean gates. And yet, they cannot compute an XOR. So this is where Rosenblatt was, was stuck, right? But we know that once you network them, you can compute an XOR. And because you can compute an XOR, you can compute pretty much any Boolean function using networks of perceptrons. This we've already seen. But then, if you look at these pictures, the way I compose my Boolean function is to add many layers, compose sub functions, keep combining them. So I have a multi-layer perceptron. I have layers of perceptrons. How many layers do I need to compute an arbitrary Boolean function? Now, to see that, I'm going to describe Boolean functions in a different way. A Boolean function is basically just a truth table. We all know this. I can write a table where I can write every possible combination of inputs and the corresponding output. So I don't need to write the combinations for which the output is 0. I just write all the combinations for which the output is 1. So in this case, these 6 combinations of inputs all generate the output 1. This is a Boolean function. But then I can write this Boolean function in disjunctive normal form. And what is a disjunctive normal form? Corresponding to each of these input combinations for which there's an output 1, I have a clause. So it says that if x1 is 0, and x2 is 0, and x3 is 1, and x4 is 1, and x5 is 0, the output must be 1. Stated in Boolean terms, not x1, not x2, x3, x4, and not x5. That's one clause, right? So that's this first guy. Similarly, the second one is going to be not x1, x2, not x3, x4, x5. I will have one such clause for every single input combination that produces an output 1. And if I OR the lot, which is shown by the plus, this is my Boolean function, right? Any Boolean function can be stated in this manner as a truth table. And so this means that since perceptrons can compute all of these ANDings and ORs, I can have one perceptron for each of these clauses, OR the lot, and then I have computed my function. So what this means is that I can compute any Boolean function using just one hidden layer. An MLP with a single hidden layer is a universal Boolean function. It can you give me a Boolean function and I can construct an MLP with one hidden layer that will compute it. So why do we need depth? If I can get away with just one hidden layer, why do we need depth? To understand that, let's go back and look at truth tables slightly differently. How many of you are familiar with Carnot maps? A small number. At least the electrical engineers amongst you must have encountered Carnot maps. Carnot maps are just a topological way of arranging inputs. So here, this is a function of 4 inputs, Wx and Yz. These are the 4 combinations of Wx. These are the 4 combinations of Yz. And what you will see is that if you look at any 2 adjacent columns, they differ in only 1 bit. If you look at any two adjacent rows, they also differ in only 1 bit. And also the topmost column and the topmost row and the bottom row, they're neighbors, they only differ in 1 bit. The leftmost column and the rightmost column are neighbors, they differ in only 1 bit. So this whole thing is like a donut, okay? This represents all 16 combinations of W, X, Y, and Z. And so each cell over here is one combination of W, X, Y, Z. So this is where W and X are 1, 1, and Y and Z are also 1, 1. That's the cell over here. And the highlighted cells are the cells for which the output is 1. So if I look at the truth table in this manner, there are 7 clauses for which the output is 1. So a simple DNF formula is going to have 7 clauses. But then when you arrange things like this, you can begin grouping things up. And so the way you group things up, you can see that, you know, if you look at the first column tells me that regardless of the value of W and X, so long as YZ is 0, 0, the output is 1. So those 4 things can be grouped into a single clause, which just says not Y, not Z, right? Similarly, if you look at this guy, it says that so long as WX is 0, 1 and Y is 0, the value of Z does not matter. The output is going to be 1. So I can group these two guys and say not W, X, not Y, right? Similarly, these two guys can be grouped into not X, Y, not Z. In fact, the 4 corners can be grouped into a smaller clause. And so although there are 7 clauses for which the output is 1, by grouping them up, I can actually make a much smaller Boolean function. Now, and that's how I can make a compact DNF formula or a one hidden layer MLP for this function. But then is there so that's what this would be like, right? But then is there a truth table which simply cannot be reduced in this manner? Anyone? What kind of truth table cannot be reduced by grouping? Any responses? A checkerboard, right? This guy. Nothing is actually going to be groupable, right? And so if I want to build an MLP with just one hidden layer for this, I will need 8 clauses, 8 neurons in the hidden layer, right? Or so this is going to need 8. Or here's a 3-dimensional version of a Carnot map. This has 6 variables. It has 64 boxes. Every alternate box is a 1. So if I want to do this with just one hidden layer, I'm going to require 32 neurons in that one hidden layer. And so this generally says that for any combination of any function of n inputs, if I have an XOR pattern of this kind, then if I want to do this with a DNF formula, which is basically a one hidden layer network, I'm going to require 2 raised to n minus 1 neurons in that hidden layer. Basically, it's exponential in the number of inputs. But then if you look at this closely, this is, if I allow multiple layers, this is actually an XOR, right? The first guy is W XOR with X, XOR with Y, XOR with Z. The second one is U XOR V, XOR W, XOR X, XOR Y, XOR Z, right? And we know that you can build an XOR using just 3 neurons. So the first guy can be built like this. I can just XOR X and Y, then XOR the result. I can XOR W and X, XOR the result with Y, XOR that result with Z. And this is going to give me the desired function. And each XOR needs 3 perceptrons. In fact, I can do it with 2. So I have 4 variables. The number of perceptrons is going to be 3 times, or actually 3 times 3, because the first one doesn't need an XOR, right? So also, for this guy with 6 inputs, I can do the same thing. And this is going to need only 15 perceptrons. Earlier, we needed 33 perceptrons, 32 in the first hidden layer, 1 in the output. But by letting the network go deep, as opposed to having just one hidden layer, what I did was greatly reduce the number of neurons that I would require to model this function. And so, more generally, an XOR of n variables is going to require just 3 times n minus 1 neurons. Compare this to 2 raised to n minus 1 neurons if you want to do this with just one hidden layer, right? So clearly, going deep is going to give you a tremendous gain in the number of neurons required. Now, a single hidden layer is going to require 2 raised to n minus 1 plus 1 neurons, which is exponential in n. But if you let it go deep, then I'm only going to require, 3 times n minus 1 neurons, which is linear in n. Now, but there's something more. Is there a limit to how deep the network should be before the network size begins to explode? And even that can be calculated. How so? I can arrange all of my XORs in 2 times log 2 layers, log 2 of n layers. How? We know that the XOR is associative. So if I have x1, XOR, x2, XOR, XOR, x3, XOR, x4, and so on, I can begin pairing these terms up. I can pair the results up, and it's going to give me the same output. So which means I can arrange the network in this manner, right? I'm going to have the first group is the XOR of x1 and x2. The next group is the XOR of x2 and x3 and x4. Their result is XORed, so I can just group this up. And so because I'm always pairing things up, then if I have n, if I'm each time I compute an XOR of 2 units, I need 2 layers, right? Because an XOR is a 2-layer network. But then I need log base 2 of n such blocks, that's all. So overall, this network can actually be arranged in, the picture is missing, 2 times, because each XOR needs 2 layers, log 2 of n layers. And that, so long as you have that depth, then the number of neurons you require to compute this function is going to be linear in the number of inputs. But what if you say, I'm not going to give you that much depth, I'm only going to give you 3 layers? Then if you put a restriction on the number of layers, here's what happens. After you can keep reducing the number of variables to a point, but then beyond that point, you're going to have an XOR of a certain number of variables, and you have only 2 more layers left, which means that you have a fixed number of layers and an XOR of an arbitrary number of inputs. So that layer is going to be exponentially sized, exponentially wide. So what this tells us is that reducing the number of layers below the minimum will result in an exponentially sized network to express the function fully. And if you try to if you say, I'm not going to give you these many neurons, I'm going to give you 1 neuron less, guess what? An XOR is a crazy function. If you miss 1 bit, the error is 50%. So just giving you 1 neuron less than this minimum requirement is going to give you a network that's completely useless, right? So what we are saying is that a network with fewer than the minimum number of neurons is going to cannot model the function. Very often, just going below the minimum required network by 1 neuron can give you a completely useless function. And the minimum required number of neurons depends on the depth. You really want the depth to be a function of the dimensionality of the input. If you have a fixed size, fixed depth, regardless of the dimensionality of the input, then it is a guarantee that there are many functions that you can never model. So deep Boolean MLPs that scale linearly with a number of inputs can become exponentially large if recast using only 1 layer or a fixed number of layers. And this is going to be not just for the kind of XOR function that we saw. What really happens is that eventually, it doesn't matter what kind of function that you have, there's a probability of at least half that at some point there's the equivalent of an XOR being computed, which means that regardless of the kind of data that you're working in, with high probability, you're going to get a network where at some point there's an XOR operation. And if you restrict the number of layers beyond that point, your network is never going to be able to compute the function. Yes. I will get to that. Right. So the question here is, does this only work with threshold activations? It's a generic concept. We'll get to it, right? So the XOR is, now the thing is, the XOR is really a parity problem, but there's a general theorem which shows that any Boolean circuit of depth D using Boolean gates and unbounded fan-in requires once you fix the depth of the network, the number of neurons you require is going to be exponential in n, or n raised to 1 over d, right? So there's also a crazier function theorem, very simple one by Shannon, who basically invented everything you can think of, who showed that in spite of all of this theory, no matter what, if you have n inputs, there's always a function, Boolean function, which requires at least 2 raised to n over n gates. But we are unlikely to encounter this in most situations. And so in summary, an MLP is a universal Boolean function, but it can represent a given function only if it is sufficiently wide, only if it's sufficiently deep, and the depth can be traded off for sometimes exponential growth of the width of the network. And optimal width and depth depend on the number of variables and the complexity of the Boolean function, where the complexity is basically can be defined in terms of the minimum number of DNF clauses in the formula for the function. So just to summarize, multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine. But a single layer network may require an exponentially large number of perceptrons. And deeper networks may require far fewer neurons than shallower networks to express the same function. And this can be exponentially smaller. Okay? Questions? Yeah. This was the disjunctive normal form, where you have one clause per combination, right? So DNF formula is telling you how many neurons you will have in the one hidden layer network, right? Okay. Now, so we've seen Boolean functions. What about its classifiers? We saw an MLP can work on real inputs, and it can model arbitrarily complex decision boundaries, right? So we saw, for example, that a single perceptron is going to model a linear decision boundary, but then I can use this networks of perceptrons to compute complicated decision boundaries by just combining these linear boundaries together, like a pentagon or a double pentagon, where I'm going to have one subnet for each pentagon and then OR them up, or something even more complex like these crazy boundaries, right? But so if I want this boundary, I can just decompose it into many polytopes, have one subnet for each of the polytopes and OR them up, right? Now, going back to the same question of depth, in the classification situation, how does depth figure, right? So can I do this, a decision boundary of this kind using, for example, just one hidden layer? Or let's take this double pentagon. Can I do this double pentagon using just one hidden layer? The way we did it earlier for the double pentagon, we had this one, right? We had two hidden layers. We had one subnet computing the first pentagon, the second one for the second, and then we ORed them. So two hidden layers. Can I do this using just one hidden layer? Now, I won't hold you in suspense. The answer is no. You can go off and try to figure this out and just work on this very trivial example and try to see if there's any way of constructing a one hidden layer network which will do it. And well, I'm lying. There is an answer, but it's not the one, it's not a good one. And so how would you do it? So to actually do it, you have to go back and look at how we compose the double pentagon. Now, before composing the double pentagon, we first composed a pentagon, right? So instead of a pentagon, let's look at a diamond. A diamond has only 4 boundaries. So the way the network would be, you would have 4 neurons, one for each of the boundaries, and then you have an OR. So what happens is that the outputs of these 4 neurons get summed up over here. And then you compare it to a threshold. And that sum is going to be equal to 4 only inside the diamond and 0 and less than 4 outside, which is why you can use a threshold of 4 and get the diamond decision boundary. So this figure over here shows the sum. And you can see that the sum is 4 within the square and less than 4 everywhere else, which is why by using a threshold of 4, you're getting the diamond. Now, if I want a pentagon, I'm going to have 5 boundaries of this kind, right? So the network will have 5 neurons over here. I sum them up, and the sum is going to be 5 only inside the pentagon and less than 5 outside, using a threshold of 5, I get the pentagon decision boundary. If I want a hexagon, same thing. Now I'm going to have 6. The sum will be 6 inside the hexagon and less than 6 outside. But here's what I want you to look at. Not the regions which are 6, but the regions which are 5, just below 6, right? Why does that matter? Because if I try to compose something that has 2 pentagons with just 1 hidden layer, right? So if I try to compose a double pentagon using just 1 hidden layer, then there are all these regions where the sum is 4, right? So I'm going to have 4 regions for the first pentagon. I'm going to have 4 regions for the second pentagon. They will overlap. And so as a result, in these regions where you don't want an output, the sum will become 8. And so you can actually have, the interference between adjacent pentagons will make sure that you cannot create the double pentagon using just one hidden layer in this manner. So what we really want is to somehow make sure that the sum outside the central region becomes as small as possible, as quickly as possible, so that you can compose things. But then, when does that sum become small? As I keep increasing the number of sides, you will see that that sum keeps getting smaller and smaller and smaller, right? This is with 16 sides. This is with 64 sides. This is with 1,000 sides, even more. So eventually you can work out the formula for it. And as the n tends to infinity, then the sum of all of these perceptrons ends up looking like this little volcano figure to the left. And the function is, the math to derive this is a little interesting, but a high schooler did it for me. Now you can actually think of, approximate it as a cylinder, right? So what you have is a network. When the number of sides becomes very large, then the sum of the outputs is going to be a perfect cylinder where the sum is n inside the cylinder and n over 2 outside. So I can subtract the n over 2 and make it n over 2 inside the cylinder and 0 outside. And now I can actually have 2 subnets, one of which composes, say, this first cylinder. The second composes the other cylinder. If I just combine the 2 subnets, magically you get a network where the sum is 2 cylinders, which are not connected with one another. And now if I apply a threshold of n over 2, I'm going to get a decision boundary with 2 circles, 2 disconnected circles. But for this to work, the number of sides that these polytopes needed became very large, tending to infinity, right? And so the way I would actually compose this double pentagon is going to be by having very large numbers of circles filling the lot. And I can make the approximation arbitrarily precise by making the cylinders, the circles, smaller and packing it more densely. And so I can get an arbitrarily precise approximation, but this comes at the cost of requiring essentially infinite neurons in the one hidden layer. On the other hand, if I just do this with 2 hidden layers, I needed only 12 hidden neurons, done, right? So as you can see, going from a shallow network to a deep network can literally take you from a network that needs essentially infinite neurons to a network that requires something that you can count on the fingers of one hand and still get a better model of the function. So again, you can see why depth matters. These things are extremely powerful machines, but at the end of the day, the architecture makes a huge difference, and this is why we really need deep neural networks, right? So now, to answer the question that you also had, let's look at a different pattern, a worst case decision boundary. And I'm going to use threshold activation networks and then generalize to other things. Consider this very simple 2-dimensional case, right? Now, this 2-dimensional classification boundary that I want is this checkerboard where I want the output to be 1 within the yellow regions and 0 in the gray regions. Now, believe it or not, the vast majority of classification problems that you will work with in real life are going to have some variant of this structure. Not so neat, but this is how they're going to look. You don't get these nice compact regions where everything groups together, right? So now how can I model this? If I want to model this decision boundary using a single hidden layer, we know that in the worst case, I can end up with infinite neurons in the one hidden layer, right? But then let's look at the structure of the problem. This decision boundary is composed of 16 lines. And it has 41 boxes, 41 yellow boxes. So I can actually say, here's what I have. You see those, each of the lines. So each of those lines can be composed, captured with one perceptron, which has a linear decision boundary. And then the subsequent layer can use different combinations of these lines to capture each of these highlighted yellow regions. And so this network with 16 neurons in the first layer for the 16 lines and 40 neurons in the second layer for the 40 highlighted yellow regions can capture this decision boundary perfectly, right? So what happens? So a neural network, we say, can represent any function provided it has sufficient capacity. This network has the capacity to model this function with 57 neurons, right? But then just suppose I decided that I'm only going to use 8 neurons in my first layer, right? Now, we've already told you that if I increase the depth of the layer, I can capture much more complicated functions with far fewer neurons, right? So suppose I decide to exploit it and say I'm going to use only 8 neurons in the first layer of this network. And I'm using threshold activations. Can I capture this decision boundary? Anybody? Would I be able to? So since you're not able to tell me, the answer is no. Why? Because I have threshold activations, right? So each neuron is only going to tell me on which side of the boundary the input lies. So by the time you go past the 8 neurons in the first layer, you're only going to be able to say in which of those strips the input lies, but it will not be able to tell you where in the strip the input lies. Now, even if your first layer neurons were not parallel and got some other structure of this kind, once you go past the input, because you have a threshold activation, the outputs are all either 1 or 0. So the only thing you will be able to say is to say which of those diamonds or the red rectangles, the red parallelograms the input is in, but not where it is within any given parallelogram. That means that the subsequent layers do not have enough information to reconstruct this decision boundary. The information is lost by the time you cross the first layer. So depth now becomes irrelevant. You can add 1,000,000 layers, the information is gone. You've lost it and you cannot reconstruct it. So this is a problem, right? There is a minimum depth below which you cannot really go because the loss of information is too great. But then, same thing. Even if I have 16 neurons in the first layer, there are 40 highlighted regions. If I'm going to use only 39 highlighted neurons in the second layer, it doesn't matter what I do downstream. I will not be able to compute this decision boundary. So at each point in each layer, there is a minimum width that the network must have for me to capture my desired decision boundary. Otherwise, it's not going to work. Now, what is the reason for this, right? A network with fewer than 16 neurons in the first layer or fewer than 40 neurons in the second layer cannot model this. This has to do with the kind of activation I chose, as I just mentioned. It has to do with the fact that I used a threshold activation. So if I have a threshold activation, each activation function is going to tell you whether you're to the left of a line or the right of a line. So if I have 4 neurons over here in the first layer, it can maybe tell me in which of those 5 regions the input is. But there's no more further distinction, which means that the subsequent neurons cannot actually make up for this loss of information. You will never be able to construct this function. So what is the information we need? It would be nice if we had some idea of not just on which side of the boundary we are, but how far we are from the boundary. And so, for example, if I used a sigmoid activation, a sigmoid activation still has a boundary to the right of which the output is greater than 0.5, to the left of which the output is less than 0.5. But then as you go further away from the boundary, the activation value changes. So it gives you an information of how far you are from the boundary, which means that the subsequent neurons now have some information which they can operate on and construct your decision boundary. But then don't be fooled. This is not everything, right? Because this gives you some additional information, and so the subsequent neurons can construct the sum of the decision boundary. But here, for example, if those were my 4 neurons and all of them were sigmoids, now all I'm able to do is to allow the subsequent neurons to construct boundaries which are somewhat parallel to the boundaries that the first level neurons gave me. I cannot go orthogonal to them. That information has been lost. And so you're always going to have this situation where once you have fewer than the minimum number of neurons in any layer, the loss of information can be unrecoverable. Nonetheless, even within this setting, if your neurons are graded, the activations are graded, which tell you how far you are from the boundary, you can hope that the downstream layers will actually learn the function. And so you really want activation functions which carry information about how far you are from the boundary for as long as possible. The problem with sigmoids is that once you go beyond a certain point, the sigmoid saturates. So at that point, the sigmoid is not telling you how far you are from the boundary, so the rest of the network doesn't have information to work on. Something like a rectified linear unit, on the correct side of the boundary, it continues to give you information forever. So this is a much more useful activation. Or if you had the leaky ReLU, it's actually going to give you information on both sides of the boundary. So that's actually going to be even more informative than a regular ReLU, and that's actually going to allow you to model boundaries, allow downstream neurons to model boundaries if the lower neurons didn't actually do the job. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but it's going to require greater depth to permit later layers to capture patterns. So questions? So here's where we stand. MLPs are universal Boolean functions. They're universal classifiers. They're universal approximators. Even a single hidden layer, not a single layer, but a single hidden layer MLP can approximate anything to arbitrary precision. But the size of the network could be exponential in the dimensionality of the input. And deeper MLPs can achieve the same precision with far fewer neurons. In other words, deeper networks are much more expressive. So here's one more thing on depth. Here's a very nice little example, right? When I'm trying to learn, so actually, it's 10:26. I think we have a break at 10:30. So I'll stop right here, and I'll pick up from here after the break. Waited to keep talking for another 90 minutes. Okay. Do me that favor. All right. So thank you again for staying with me so far. I will take any questions. I was taking some questions during the break, and if you have any additional questions, I'll take this after the lecture. But then let me continue. So this is where we were, right? We saw that MLPs are universal Boolean functions. They're universal classifiers. They're universal function approximators. Even a single layer MLP can approximate pretty much anything. Deeper networks are more expressive. But then we're going to switch to an assorted set of topics on how to make the network model a given function. What we have seen so far is that the network can model anything, but not every network is going to model everything, right? You have to actually make the network model a given function. So what we found is that the network can approximate any function, but first the network has parameters and the architecture have to be set so that it computes the function. Then how do you set it? You can try to learn this, but to learn this, the function that you're trying to model must be known a priori. So if I know that I'm modeling an XOR, I know I have to set the weights to +1 and -1 and things like that. If I don't know what that function is, how do I learn it? So here's what you have. You assume that you have some arbitrary function shown by this grid over here, and which I'm calling g of x. And then you have a network, and the parameters of the network are the weights and the biases of the neurons in the network. And so the network itself is a parametric function whose parameters are these terms w. And the question is, how do you set these w? Pardon me? Oh, sorry. So the question is, how do you set these parameters w for the network to model this particular function? So at a high level, here's what you have. Let's say that blue dotted line represents the function that you want the network to learn. Now, if I set up my network, I'm assuming that the architecture of the network has been provided, that I know I've made it sufficiently expressive that it can model this function. And now, for some arbitrary setting of the weights, the network is going to give you a completely different function, maybe the one shown by the dotted red line. So now there's an error between the function that you want to model, the blue one, and the function that you are modeling, which is the red one. And so the shaded area shows you the error. And what we want to do is to set these network parameters w to minimize the shaded area. That's basically what our whole objective of learning a network is all about. And of course, to quantify the shaded area, you first need to define some error, which tells you what the difference is between the actual output of the network and the desired output of the network at any point. And then the overall error is going to be the integral of this error over the entire input space. So if you want the entire shaded area, you're going to be integrating the function, the error function over all of x. And then you want to set the network parameters to minimize this total error. The problem for this, for me to be able to perform this optimization, my function g of x must be known everywhere. Otherwise, I'm not going to be able to compute this error, and I'm not going to be able to minimize it. So instead, and you're never going to have such specification. If the function were known, why would you waste your time learning a neural network for it? You wouldn't do it, right? So what we have in reality is that you have a few snapshots of the function. Here's the value of the function at this given x. Here's the value of this function at this other x. And from these few snapshots, you have to learn the entire function. So, again, using this one-dimensional example, I will not have the entire shaded area. I don't have a specification of the blue dotted curve. Instead, for a number of inputs, x1, x2, x3, x4, x5, I will know the desired value of the function. This is just collecting your training data, right? And so at those x's, I know the desired outputs, D1 through T5. I know the current output of the network, which is given by the f's. And so what I can compute is the average length of all of those little red segments. And what I will be doing is to train the network to minimize this average length and hope that in so doing, I'm actually minimizing the entire shaded area. You can see the risks with this, right? But I'm going to assume that I don't have to go through the risks. You get an idea of how this works. So the real problem that we deal with is find the network parameters that fits the training points exactly, which is the empirical error at just the training points. And the hope is that if you do this, it learns the function everywhere, the entire curve over the entire input space. So the general approach, at each of the training instances, you will define an error between the desired output, which you have measured, and the actual output of the network, which you can compute. And then and the error can be different kinds. If you're doing a regression, you're going to just look at maybe the squared error. If you're performing classification, and we'll get to that, it's a little more interesting, you're going to say whether the classifier output is correct or wrong. And then based on that, you're going to adjust the parameters to make sure that the network learns the right thing. But then there's nothing stopping the learning algorithm from learning something of this kind. You want to learn the dotted blue line, you could end up learning the red line, which is a perfect fit at all of your training points, but complete garbage everywhere else. And so this means at this point, you need to begin assigning some constraints on the model. And this is where we go off the deep end and go from knowing the function to hypothesizing the nature of the function. And the hypotheses you make are going to decide whether the function that you learn is any good at or not. And the functions that the hypotheses that we've most often made are that our functions are smooth, that they don't vary randomly, they're not noisy. And so we make assumptions of smoothness, and empirically we found that this makes sense. In a structured world, smoothness makes a lot of sense. If the functions we want to learn were not smooth, there would be noise. There's probably no value in predicting them anyway. But then here's the problem, right? This picture is highly optimistic. How much data do we actually have? I will give you an idea. So let's consider a very simple case where all my inputs are binary, just 0 or 1. And let's assume that I have inputs 100 dimensional, which is very small. In the real world, your inputs are thousands of dimensions, and they're continuous valued, right? So if I have binary inputs and just 100 dimensions, my inputs are going to live on the corners of this hypercube, this 100-dimensional hypercube. And in order to specify the function fully, if I want to learn this function, I want to specify the value of the function at every corner of the hypercube. How many corners will this hypercube have? It's going to be 2 raised to 100, or approximately 10 raised to 30. So if I give you 10 raised to 15 training points for this very, very, very simple function. Now, how large is 10 raised to 15? It's like what? 1,000 times tera. Absurd, right? Nobody ever has 10 raised to 15 training points. But if I give you 10 raised to 15 training points, it's like giving you no training data at all. You're off by a factor of 10 raised to 15 in specifying this very simple function. That is huge. To give you an idea of, if I scale things back all the way to 1 dimension logarithmically, it's like saying, here is this function of x, and here's this one training point. Now find me the function x. That's literally what we are doing. So I can, here's another way of thinking about it. Suppose I just scattered my 10 raised to 15 training points on the corners of this hypercube. And let's assume that each edge of the hypercube has some finite length. And suppose you sat in a really, 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 really small spaceship. And the spaceship was only allowed to travel along the edges of this hypercube. And you're allowed to approach arbitrarily close to the speed of light. And then I place you on one training point that you have specified, and I let you travel along the edges of the cube until you find the next training point. The universe will end before you find the next training point. That's how rare your training data are. And based on that training data, you're actually trying to learn something as complex as, I'm going on the wrong computer? Yeah, this, right? Or this, or in high dimensions. So you can see the kind of completely idiotic and absurd problem that we start off with, and somehow we magically solve it. So once you do that, once you realize that this problem is absurd, you have to begin making assumptions. And the one big assumption we're going to make is smoothness. So the assumption we make is that whatever the function is, it's a real life function. It doesn't change randomly. It is not noise. So there are many different ways of imposing this constraint of smoothness. I won't get into most of those. I'll talk about the one constraint that we did relates to what we were talking about earlier, which is depth. So why are deep networks useful? Now, mathematically, anytime you have one layer of a network, you're transforming the input using some weight matrix. And the weight matrix has, regardless of the weight matrix, it's going to have a small number of singular values above 1. The majority of them are going to be smaller than 1, which means that when you transform the input is going to shrink. So every time, every single layer of the network is basically flattening the surface, the topology of the function that you're learning. And so as you keep adding more and more layers to the network, the topology of the network the function gets smoother and smoother and smoother. And as we found, this actually ends up being more generalizable. So here's an example that I can show you. Here are 2 decision boundaries, which one of them is the shape of an arrow, the other is a square within a square. And we had some optimal neural networks, which is the correct architecture. We know we can manually set the configurations of these networks to get these decision boundaries. And then we drew like 10,000 samples from these decision boundaries and tried to train the network. And here is where I have to actually thank Pulkit Agarwal and MIT for these pictures. But here is the decision boundary that we actually learned. It's garbage, right? So, but then let me do something else. Here's a different decision boundary. I'm going to start off with a network, and I've decided that I'm going to use 660 neurons. So if I can arrange those 660 neurons in different ways. I can arrange them in 3 layers of 220 neurons, hidden layers. I can arrange them as 4 layers of 115 neurons. I can arrange them as 6 layers of 110 neurons, right? 165, 110, 11 layers of 66 neurons. And as you can see, as the network for the same number of neurons, as the network gets deeper rather than wider, the model is able to capture the decision boundary of interest much better. In fact, you can see that it's actually doing a pretty decent job of capturing the decision boundary that looks like the bear. So this is one way of doing it. Basically, you increase the depth of the network as opposed to the width of the network. It imposes smoothness constraints, which allows you to learn boundaries and functions much better. There's another way of doing it, which is you simply increase the amount of training data. In this case, if you go from 1,000 training samples to 10,000 training samples, it doesn't really matter what you do. It actually learns the boundary quite nicely. But you're never going to get, as we saw in real life problems, you're never going to get that scale of data, right? So just again, this is extending the notion of the architecture. But then going back, what does the network really learn? So you're given a collection of input-output pairs, and we are supposed to learn the function. So if I go back to my double pentagon example, this is the function that the network is supposed to learn. It's going to output a 1 inside the double pentagon, 0 outside. I'm not a very good artist, so the picture looks horrible, but should convey the idea, right? So in reality, so the assumption is that you're going to get training data which are all 1, samples of training data which are all 1 inside the double pentagon and 0 outside. In reality, it's never going to be that clean. The boundaries, your decision boundaries in real life problems are always fuzzy. So you're going to get some blue colored dots in the red regions, the boundaries of the red regions, some red colored dots in the boundaries of the blue regions. And so we're going to have to learn our function from these training samples, the stars that I have on the left picture. And how do we do it, right? So let's dial the whole thing back to a single perceptron. And again, I'm going to use a threshold activation function. As we saw earlier, going from a threshold activation function to other functions doesn't greatly change the intuitions we develop. So let's stay with threshold activations. Now, a single perceptron models a linear decision boundary. And so it's learning the hyperplane such that everything on one side is a 1 and everything on the other side is a 0, right? So it's learning a step function in the space. Now, you want to learn this just from data examples. So nobody's actually giving you the function and saying, okay, go find me the perceptron weights that learn this function, right? So you're given just some samples like these red and blue dots, and you're told to find the Heaviside function that correctly puts the red dots on one side of the boundary and the blue dots on the other side. So you want to learn that function, the Heaviside, the step function, such that the blue dots fall on one side and the red dots fall on the other. Now, Rosenblatt himself came up with an algorithm for this, and we're all familiar with this. This is the perceptron rule, and it's based on a very simple principle. First, you want to find a set of weights and a bias and a threshold such that if the weighted sum of inputs exceeds the threshold, the output is 1, otherwise it's 0. Now, instead of having a separate threshold and a weight makes things a little ugly. So I'm going to convert this affine function to a linear function by saying having a separate threshold is the same as having an additional input component, which is 1. And the weight of that input component is going to be the threshold, right? So I've just modified this problem. And now, here is what our perceptron looks like. I'm saying I'm looking at the weighted sum of inputs. If the weighted sum of inputs is positive, I'm going to call it class 1. If the weighted sum of inputs is negative, I'm going to call it class 0, right? So, but then how can I think about it? The weighted sum of inputs, basically I want to find the hyperplane, which is to say the weights such that summation wi xi, the weighted sum equals 0. That is the equation of the hyperplane. And I want to find the hyperplane that perfectly separates class 1 from class 0, right? Now, let's look at it from a linear algebraic point of view. What is the weighted sum of inputs? I can think of the weights as a vector. I can think of the input as another vector. So the weighted sum of inputs is going to be just an inner product between the weights and the input. When is the inner product between two vectors 0? When the two are at 90 degrees to one another, right? So when I say the W transpose X equals 0, it's the equation for all vectors X that are orthogonal to my weight vector W. And so you're really looking for the weight vector W. The weight vector W specifies the plane, and you want to find the weight vector W that separates the red dots from the blue dots. This is a simple concept, right? But then here's the next concept. Suppose if I look at this thing and the weight vector points in some direction, then the hyperplane where the W transpose X equals 0 is going to be at 90 degrees to the weight vector. Now, all the data on the same side of the plane as the weight vector are going to be such that W transpose X is positive, because W transpose X is basically a cosine and the angle is at 90 is less than 90 degrees. All the data points which are on the other side of the plane from W are going to be ones where W transpose X is less than 0 because the angle is greater than 90 degrees, right? So simple concepts. Now, suppose I give you a single training instance and I say, find me the weight vector. And I say this is a single training instance from the positive class. And I say, find me the weight vector that exactly perfectly classifies this training point. Now, the best weight vector, which gives the maximum separation of this plane of this point from the plane, is going to be the data vector X itself, right? It's going to point directly at the vector X, and the plane is going to be at 90 degrees to that data point. So for an instance from the positive class. So for a positive class instance, the best weight vector is plus X. For a negative class instance, the best weight vector is minus X. You want the weight vector to point exactly away from the vector so that this vector lies as far as possible from the boundary plane on the negative side. So very simple concept. Now, let's put this together into our perceptron training room. So what we will say is, anytime we are going to keep adding the training data points, we are going to basically adjust our weight vector towards the optimal weight vector for every training data instance. I have the algorithm over here, but it's best done pictorially. It's an iterative algorithm. I can start off with a random initial weight vector, and the random initial weight vector is going to give you some decision boundary. Then I begin classifying my data instances until I find a data instance that is misclassified. Now, this data instance over here is here blue is positive in my picture. It's a misclassified positive data instance. For this data instance, the ideal weight vector would have been that vector itself, right? So what I will do is simply add this weight vector to my original, vector X, to my original weight vector. Basically, I'm pulling the weight vector towards the ideal vector for that misclassified data instance by just adding it. And now I have a new decision boundary. Then I can continue classifying my training data instances. Eventually, I'm going to find some other data instance which is misclassified. Maybe this is my negative class data instance. For this negative class data instance, the ideal weight vector is going to be exactly 180 degrees pointing away from that vector. So I'm going to add that to my current weight vector, and I'm going to be dragging the weight vector towards the optimal decision boundary for that training instance. So training instance by training instance, I'm going to check it. If it is correctly classified, there's nothing to do. If it's misclassified, I will drag the weight vector towards the optimal weight vector for that one training instance. And eventually, if your classes are linearly separable, you can show that this is going to give you a decision boundary that perfectly separates the two classes. So it's a very simple rule. Everybody is familiar with the perceptron learning rule. And moreover, you can actually prove that this will converge and give you the correct solution in a finite number of steps. but under one condition. And the condition is that the classes must be linearly separable. If the classes cannot be separated by a hyperplane, you will keep finding misclassified instances, and you're going to keep going on forever, correcting and correcting and correcting and correcting, because there isn't a plane that's going to classify things correctly, right? So far, so good. Now let's consider this double pentagon problem, right? So let's assume that we're working with linearly separable data. This works. The perceptron learning rule is great. But then let's come to this double pentagon problem. In this double pentagon problem, I've given you, and let's say it's perfectly classifiable. I don't have noise. So all the red data points are inside the pentagons. All the blue data points are outside the pentagons. Now we know that I can actually construct a network of this kind, which classifies this double pentagon data perfectly, right? Now, let me assume that I have the perfect architecture. And let's look at what each of these neurons is actually doing. So if you look at the ideal classifier for this double pentagon, each of the lower first level hidden layer neurons is going to be capturing one of these lights. And then the upper neurons are just ORing and ANDing these things, right? So let's assume that the entire network has been given to you. The parameters of every single neuron, except the one highlighted in yellow, have been given to you. And now you want to learn the parameters of this highlighted neuron so that the overall network captures this double pentagon. Can we do it using the perceptron learning rule? What do you think? Over here. Anyone? Why? How? So the point is that the perceptron learning rule cannot work if the data are not linearly separable, right? And the blue and the red dots here are no longer linearly separable. That line doesn't exactly separate the blue and the red dots. So even though a perfect classifier exists, you cannot find it because for this particular neuron, the data are not labeled in a manner in which you can find the boundary. To find the boundary, you have to do something. You have to relabel your data and paint all the blue guys on the wrong side of the boundary red. And now you can learn your boundary. But the real problem is you don't know which data points to label, right? Nobody's giving you that truth. So the only way to actually learn this classifier is to try out every possible way of relabeling the data. So of the 12 neurons, I've given you 11. I'm asking you to find one neuron. Of the 13, I'm giving you 12. I'm asking you to find one neuron. And just the task of finding that one neuron is going to require you to try every possible way of relabeling the data until you find a labeling such that when you learn the boundary, the overall classification error is 0. So this is not a feasible solution, right? This does not work. So which is why, even though we know a solution exists, even though we have an algorithm for finding the solution, something that gives us this correct answer, this business of trying every possible way of relabeling the data such that we can learn a line that keeps all the red dots on one side and the blue dots on the other side makes it impossible because we don't know how to relabel the data. And so, now if I make this even more complex and I say that learn the entire network, not just one neuron, then for every one of the neurons, you're going to have to test every possible way of relabeling the data. And you're going to have to test every possible combination until you actually learn a bunch of boundaries that captures the double pentagon. So here is a very trivial problem. And on this very trivial problem, basically trying to use something like the perceptron learning rule to find the optimal classifier, which exists and can be found, is computationally infeasible. It's not going to happen. So in fact, we need to know the desired output of every neuron for every training instance. And basically, you want to relabel the data such that the output for each neuron is linearly separable. And then these boundaries must combine to give you the decision boundary that you want. It's not feasible. And that actually causes this problem. Training the network using the perceptron rule is a combinatorial optimization problem, because when I just give you the training data, I'm not giving you the outputs of the individual neurons. So we have to find out the optimal outputs of the individual neurons for me to be able to train the entire network. So which means that I must also determine the correct output of every neuron in the network. And this is exponential complexity. And so what happened was, somewhere in the 60s and 70s, people realized that, yeah, multi-layer perceptrons can model pretty much any decision boundary. But finding that decision boundary is a combinatorially a hard problem. In fact, this is not going to be solvable. We are dead. And so research in the area kind of died. So, going back to the history of why we waited until 2016, at various points, we kept running into these roadblocks. So, but then there was this insight that Paul Verbos and MIT had in the late 70s, early 70s. And the problem we realize is that if I am trying to train my classifier, what am I training my classifier for? I am training my classifier to minimize the classification error on the training data. So if the classifier output is 0 and the desired output is 1, then I have an error of 1. If the classifier and desired outputs are both the same, then I have an error of 0. And all I am doing is counting the errors, and I'm trying to minimize the count of errors. So let's say these are my training data, x1 through x5, and the green line is my ideal classifier, but the dotted blue line is the current classifier that I've got. So the dotted blue line is making 2 mistakes, so I have a total error of 2. But then, I don't have a way of inspecting this data, right? So just by looking at this, is there any way for me to know whether shifting the dotted curve to the right is a good thing to do or bad? There's no way for me to know that, because I can keep shifting it to the right for a long distance. And until it crosses the next training instance, I don't really know that the error is increasing. I can keep shifting it to the left also for a long distance. And until it actually crosses a training point, I don't know that the error is decreasing. So you have this issue that just perturbing the classifier, parameters of the classifier, gives you no indication at all whether you're doing the right thing or the wrong thing. So same thing, if you go to, that was for one dimension. Once you go to a higher dimensional problem, it becomes even more complex. You're sort of wiggling all of your decision boundaries, and you can wiggle them a whole lot and not see any change in the classifier output. Okay, once again, because as we saw, your training data are very, very sparse. It's not like you can wiggle it a little bit and it's going to cross a boundary. So as you get on larger problems, this problem becomes much more challenging. Now, let's go back and try to look at the problem why. The problem arises because we are counting errors. We are counting errors because that's what we want to minimize. We want to make a classifier that makes the fewest errors. So you want to count how many errors are being made, and you want to adjust the network parameters until the total number of errors is minimal, right? But counting errors has this problem that, moving things doesn't tell you whether eventually the error is going to decrease or increase. So instead of simply counting errors, we are going to change our threshold. We are going to do a bunch of things. We are going to change our threshold activation to a continuous activation, number one. And then we are going to change the manner in which we count the error. So here's what we do. The upper network, the upper picture, shows you what you would be doing if you were counting errors. The dotted red line is what you'd have with the threshold activation. And you can see, as you can see, when the threshold activation has a threshold of T1, it's making 1 error. If I move it all the way from T1 to T2, it's still making 1 error. The fact is I have to continue moving in that direction. But if I can't count the errors, it gives me no indication that this is the error direction in which I have to move. So instead of using a threshold activation, I am going to be using the smoother activation given below. And instead of counting errors, I'm actually going to look at the distance from the actual output of the network to the desired output of the network, the dotted length of the dotted red lines. And the sum of the length of these dotted red lines is what I'm going to be using as my objective. Now, keep in mind that this objective is not the same as the one above. It's a proxy. We are using a proxy objective. And the nice thing about this proxy objective is that when I've moved the network left, you can see that the total length of the dotted red lines decreases. And so you get an idea of that this is a correct thing to do. But the problem is that this is not the real objective. This is a proxy objective. And the answer it can give you will often be wrong. So although this proxy objective gives you a way of manipulating the network parameters to move in the correct direction, there is no guarantee that it's actually going to minimize the true objective, which is the error on top. And I'll let you think of examples why this is the case. So this is issue number one. Second, what do we actually model? In real life, data are rarely linearly separable, right? And Rosenblatt's learning rule wouldn't even work. So even for a single perceptron, here's what you're going to have. I'm trying to learn this Heaviside function, but it's not that I have only red dots on one side and blue dots on the other side. I'm going to have blue dots sitting on the floor on the red side and some red dots hanging in the air on the blue side. And in spite of this, I'm going to have to learn my Heaviside function. And so when I try to learn a network, crazy things can happen. So to give you an idea, let's work with a one-dimensional example. Then here are some example data, ones and zeros, right? So you have two classes, the red class and the blue class. I want to learn a classifier, and the optimal classifier is a threshold for this particular example. But then if I have an entire network, I know that my neural network is a fantastic approximator. It can learn any function. There's nothing stopping my network from learning this useless function, right? So how do I prevent this? How do I prevent? Now, I think everybody will agree that this is not what we want to learn. We want to learn something different. We want to learn a boundary where things to the right are best classified as red and things to the left are best classified as blue. So how do we deal with this? Even if I say that this is okay, this is really what I want to learn. I want to learn a network which just gives me, crazily follows the training data. Then I give you this training instance where I have two training instances which are exactly the same X value, but different Y values. What will the network output over here? Is it going to be 0? Is it going to be 1? Or even if I say, I'm going to be choosing something, right? Now, let's just say this is not a realistic case, so I don't care. That's fine. But then what if these data are slightly perturbed and say that although they are not identical, they're only off by 10 raised to minus 17? Then would it be okay for me to learn a model of this kind? It doesn't make sense, right? And so you have this situation where the infinite capacity of the network means that the network can learn any odd rubbish. And that's not what you really want. So we have to change our perspective. The way we will change our perspective is like this, right? I'm going to say, okay, let me count how many training instances I have at this particular value of X. So if I have 90 instances of 1 and 10 instances of 0, then I can decide, right? But again, here's the decision. If the majority is 1, should I simply be outputting 1 or should I be outputting 0.9? So it makes a lot more sense for me to be outputting 0.9 rather than 1, which tells me that 90% of the data at this particular X are all 1, right? But then let's go back to the 10 raised to minus 17 example. I don't have 100 data points at exactly the same value of X. I have 100 data points, but they're all slightly perturbed with respect to X. And 90 of these are 1 and 10 of these are 0. Now, does it suddenly become okay to go up and down? Or should I still be outputting 0.9? It makes sense that if the perturbation is small enough, I should still only be outputting 0.9, right? At what point does it become okay for me to output something different from 0.9? So here's how we're going to change our perspective. I'm going, instead of looking at just the actual output, the desired output at any given x, I will look at a slight window around that x. And then I will claim that the desired output is the average y values for all of the instances within that x. And then as I go from left to right, over here, everything is blue. So the desired output is 0, 0, 0. Then here, I begin seeing a few instances of red. So the desired output begins shifting towards red. And then eventually, everything I see is red. And so this is the kind of output I really want, right? The question you're naturally going to ask is, how big is this window within which I count? We actually don't have to specify it. The whole point is this, that we really want a function that sort of gives you the expected number of instances at that point which have the class value 1. So what is this function actually computing? If I tell you that 90% of the training instances at this particular value of x are the class 1, what you are really saying is the probability of class 1 given x equals 0.9. So this function is computing the a posteriori probability of class 1 given x. And that, it turns out, is actually looks like the sigmoid, right? And so the sigmoid has a, or the softmax has a very special interpretation, that it is an estimate of the a posteriori probability of the classes given the input. Number one, okay? So let's hold this thought. When I'm training a perceptron and I use a sigmoid activation, basically what I'm really doing is I'm learning a logistic function, this which computes p of y given x for the class, right? And so that's basically what it's doing. Now, this was for a one-dimensional case. The same thing holds when the input is in multiple dimensions. Say if I have 2 dimensions, then the reality is that you're going to have red dots on the blue side, blue dots on the red side. And so what you really want to learn is a function of this kind, which gives you the probability of class 1 given the input at each point. And that's basically what the sigmoid activation computes, or the softmax activation computes. It computes the a posteriori probability of the class given the input. Now, fine. But then the question comes back to, what is the size of that window? I said that I'm going to slide left to right. I'm going to look at a small window around the current input, and I'm going to specify what fraction of inputs within that window belong to class 1. What is the size of the window? It turns out I don't even need to consider the size of the window. I can actually just use a simple statistical estimation procedure, right? So here, my sigmoid has this equation, 1 over 1 plus e raised to minus w0 plus w1x. I won't go into the math, but you're all familiar with it. And when x is very negative, it's 0. When x is very positive, it's 1. And it smoothly goes from 0 to 1, right? This is the posterior probability of y equals 1 given x. So the posterior probability of y equals minus 1, which is the other class given x, is going to be 1 minus p of y equals 1 given x, which just ends up being exactly the same as the sigmoid. The only thing that changes is that the sign of this guy goes from being minus 1 to plus 1. So I can combine these two into a single formula, and I say the posterior probability of any y given x is simply 1 over 1 plus e raised to minus of y times this affine term. So I'm not going into the math, but you're all probably very familiar with this, right? And so here's how, for the sigmoid, I can write it. I can write it in a manner which computes the posterior probability of the class y given the input x. And now, when I give you a collection of training data, xy pairs, then I know that my perceptron is computing the posterior probability of y given x. Now, there's a very standard procedure technique for learning, estimating probability distributions of data from data instances. And that's the maximum likelihood principle. You would have some kind of a parametric form for your probability distribution. And you're going to learn the parameters of this distribution to maximize the probability of the training data. Now, the joint probability of the training data is assuming all the training data instances are IID. The joint probability is simply going to be the product over all training instances of the probabilities of the individual training instances, P of xy, which I can separate out as P of x times P of y given x. And P of y given x was my sigmoid, and there's a P of x that comes out. So if I look at the log likelihood of the training data, basically it simply becomes the log of the probabilities of the training data minus the summation of the logs of the sigmoid at all the training instances. Now, what does this have to do with our standard training procedures? When I write it this way, this guy here, the term that we are actually minimizing when we perform maximum likelihood estimation, is exactly the same as the cross entropy loss that you minimize when you train your neural network. And so it turns out that what you're really doing, you're solving this, you need to solve this using gradient descent. But basically, anytime you train a single perceptron or a neural network, you're actually performing maximum likelihood training. You may not have been informed of this explicitly. You are performing maximum likelihood training of a model, parametric model, where the parameters of the model are the parameters of the neural network, such that it does the best job of computing the posterior probability of classes given the input data. So that's for a single perceptron, right? But what happens when you have nonlinear classifiers of this kind? So, or when you have complicated decision boundaries, the same concept still holds, but let's go about it one step at a time. So let's first assume that the data are cleanly separable, right? If the data are cleanly separable, then all the red data points are within the double pentagon in my example. All the blue data points are outside. And let's just assume that I have the perfect classifier. So the perfect classifier looks like this. I have one subnet for the first pentagon, one subnet for the second pentagon, and then I'm ORing the two using the final output classifier. But then I know that my output classifier is a linear classifier, right? Because we saw that each of the individual perceptrons is a linear classifier. It can separate things according to a linear boundary. Is everything to the right of this boundary or the left? That's all individual perceptrons can really do. So if this network is doing a perfect job of separating the red dots from the blue dots, then what can we say about the inputs that come to this final perceptron? The inputs that come to this final perceptron must be linearly separable. Otherwise, that final perceptron cannot separate the red dots from the blue dots. And so what the real network, what the network has really got is something of this kind. You have the lower portion of the network, which transforms the input and puts it into some y1, y2 space, where the red dots and blue dots are linearly separable. And then the final classifier can learn to separate them. So you can actually think of the entire network as composed of two components. First is the lower portion of the network, which manipulates the data and moves it around so that they become linearly separable. And then the final classifier, which actually classifies the data using a linear classifier. So, which means, of course, that once you know this, you know that the lower portion of the network is separating the data. The final classifier can be trained using any objective for linear classifiers, including maximum likelihood, max margin, what have you. So this is when the data are perfectly separable, or if your network's architecture is sufficient to separate the classes. What if the data are not separable? Or what if the network's architecture is not sufficient to actually separate the classes? In that case, the whole thing still works. The lower portion of the network is going to keep moving the data around until they're as close to being linearly separable as possible. And then the output neuron is actually going to separate the classes. So mathematically, basically what happens is that if I had a sigmoid activation for the output neuron, the sigmoid activation is computing the sigmoid on the y computed by the earlier portion of the network, but the y is deterministically computed from the input x. So which really means that when I actually train this entire classifier, I am still performing maximum likelihood estimation, except I'm performing maximum likelihood estimation not just of the final output perceptron, but also all the parameters of the network itself, such that the network can correctly compute the posterior probabilities of the classes. And that holds even for more typical settings where the classes are not linearly separable. Even here, if you actually look at what will happen, the lower portion of the network, which I call the feature extraction component of the network, it transforms the data such that the posterior probability can be most accurately computed using a sigmoid. Posterior probability of the classes can be most accurately computed using a sigmoid. And overall, so we have the situation where the feature extraction data layer transforms the data such that the posterior probability can be modeled by a sigmoid. The output logistic computes the posterior probability of the class given the input, and the entire thing is still a maximum likelihood estimator, which learns to compute the posterior probabilities of classes. So again, all of this was just to give you an idea that although we thought of this network as things in terms of connectionist networks and how it can learn functions and so on, eventually it turns out it's a statistical machine. It's actually learning to compute the posterior probabilities of classes, and every training paradigm that we are using is actually a maximum likelihood estimation procedure, which is statistically optimal in some sense, and it learns to find the best set of parameters to compute the posteriors. Now, so the story so far is that classification MLPs actually comprise two components: a feature extraction network that converts inputs to linearly separable features, and a final linear classifier that operates on these features. And training the MLP is actually a statistical exercise that finds the parameters that maximize the conditional probability of the classes given the input. Now, so far, so good. There's a lot of math, statistics, and if it hasn't put you to sleep, if I continue in that line for another 5 minutes, it will, right? So let's look at it from a better perspective, right? What's happening? Again, the whole point was I can think of the network as having two components. One is everything until the classification layer, which converts the inputs such that they are almost or perfectly linearly separable. And then the final output layer, which actually performs linear classification. But then what happens within the lower blocks of the network? How does it actually convert the input to be linearly separable? So for that, I'm going to show you a very simple example. So here is an example where I'm trying to model a circular decision boundary. So I want the network to output 1 for any data within the circle and 0 for any data outside the circle. And this is a single network with one hidden layer with 3 neurons with a tanh activation. So now look at what happens. The input is in 2 dimensions, right? So, but then the first operation that happens is that I'm multiplying this by a weight matrix, which because I have 3 hidden neurons, it's going to go from 2 dimensions to 3 dimensions. So the input is a 2-dimensional plane. After multiplication by the first weight matrix, it's a 2-dimensional plane in 3D space with some arbitrary orientation. Then the tanh activation is going to take this plane and it's going to distort it because the tanh is a nonlinear function. And then, so now what was a plane became some kind of a crazy surface in 3-dimensional space. Then the next class operation is a weight matrix, a weight vector, which takes points, which sort of projects this surface onto a line, because once I compute the weighted combination of these 3 outputs is just a single scalar, right? So the next weight vector projects this onto a line. And then the final output network tries to find out where it can put a threshold on this line so that it can classify the 2 classes. And so you can see how this happens, right? So you can see that in the training the network, it's trying to see how to position this two-dimensional plane in three-dimensional space, such that when that plane is distorted using a tan-H activation and projected onto a line, which is also being learned, all the blue dots fall on one side and all the red dots fall on the other side. And if you do a perfect job, then you're going to get a perfect classification. So it's the kind of search that is actually going on, right? At each step, you're going to try to position the data in a new space such that when you actually do the nonlinear transform that the activation requires, the resulting data after projection can be linearly separated. So, here again, you can see how this happens. It's very pretty. This is a very simple 2D case. You can actually visualize what's going on. So here's another one. This one was the CIFAR 10 data. And each of the red dots, each of the colored dots is a different class, different digit. This is an 11-layer network. And you can see initially, and then we have just looked at the data and projected it down to 2 dimensions for visualization. So you can see how the data look, all the various classes look when the training begins. But then as the training proceeds, this animation is a bit too quick. You can see what happens. As the data go through the layers, the classes become increasingly linearly separable. And by the time they get to maybe this 8th layer, they're all actually linearly separable. Subsequent layers simply increase the gap between the classes. I can do the same thing in 3 dimensions, so you can see this much better. And you can see that what is really happening is that the data, as you go through the layers of the data, each of the layers is increasing the linear separation, transforming the data and moving it around such that the linear separation between the class, they become increasingly linearly separable. And typically what happens is that the classes finally become linearly separable way before the output layer. So in this case, by the 8th layer, the classes are already linearly separable. After that, subsequent layers are just increasing the gaps between classes. So in fact, if you were trying to save computation or prune your model or some such thing, you could train your 11-layer network and then throw away the final 3 layers and just retrain your final classification layer, and you're going to get the same performance on these data because by the 8th layer, the data are already linearly separable. So basically, each of the layers keeps increasing the linear separability between the classes. So again, all of these is looking at the data. First, we saw it from a purely statistical point of view. Then we looked at it from a geometric point of view. What's happening to the data? How are they being moved around for the classification to happen, right? But then let's take yet another look. Let's look at this from a semantic point of view. And so what kind of semantic point of view can we take? We've seen what the network learns over here and over here, and we're going to try to figure out what the network learns lower down, okay? Now, recall that the basic perceptron is simply looking at the weighted combination of inputs. I'm still going back and talking about the threshold activation function. So the basic perceptron looks at the weighted combination of inputs and compares it to a threshold. If it exceeds the threshold, it outputs a 1. Otherwise, it outputs a 0. So what is this business of computing the inner product between 2 vectors? It's basically just computing the correlation between the 2 vectors, right? So here, for example, we saw this earlier. If my weight matrix, so here's a very surprising fact. In high dimensional spaces, all vectors are basically the same length. That's because if you limit the length of the vector, then if you consider, in high dimensions, if you consider any sphere, pretty much the entire volume of the sphere lies very close to the surface. So which means that if you pick a random vector in high dimensional space, it's going to be almost the same length as any other random vector. So in high dimensions, if I'm looking at the inner product between the weight vector and the input vector, then basically all I'm doing is computing the cosine between the two, because the lengths of the 2 vectors are the same. And so when I say that the neuron is going to fire, if the weighted sum of the inputs exceeds a threshold, I'm saying the neuron will fire if the inner product between the weight vector and the input exceeds a threshold, which means that the neuron will fire if the angle between the weight vector and the input is less than some threshold. So the weight vector represents a template, and there's a little cone around the weight vector, and the neuron is going to fire anytime the input falls within this cone. So you're literally matching the input to the weight vector. And so if I were to be building, for example, a digit recognizer for the digit 2, as we saw earlier, all I would need to do is, and for, in the standard LED grids, all I would need to do is to set my weights to be the shape 2 on the grid. And then when I get an input, I can just do a component-wise product and multiply, product and sum, which is the inner product between my input and the weights. And if this exceeds a threshold, then I say yes, otherwise I say no, right? So it's very simple. So what does this mean? It means that if this neuron fires, if this perceptron fires, I have found an input which looks more or less like the digit 2, right? So let's try to generalize this. Let's say I am trying to build a classifier which looks at LED grid patterns and decides if the input is a valid digit or not, right? So if that is the case, then I would expect that the lower level neurons are all going to find patterns which are typically digits or not digits. So for example, you know that if it's a digit, it's going to get these horizontal and vertical lines at the edges and in the middle. If it's not a digit, then you're probably going to get some kind of a diagonal line across the entire grid. So these are all the key patterns that clearly distinguish whether the thing is a digit or not, right? And then you have the subsequent layers, which are looking at combinations of these guys to decide on the final logic. Is this a digit or not? The key point is that this first layer of neurons is basically just a bunch of correlation filters. Their weights are looking for very specific patterns. If this neuron fires, then there's a guarantee that there's a horizontal line on the top in the input. If this neuron fires, there's a guarantee that there's a horizontal line of pixels at the bottom of the input, right? So also if this one fires, you know that there's a vertical line. So here's what I can do. I train the network, right? And then after having trained the network, I do something very simple. I check if this neuron has fired. If this neuron has fired, I go and draw vertical line on top. If this neuron has fired, I draw a vertical line at the bottom. So I can reconstruct what each of these neurons has detected. I can put together a blank LED grid, and I can reconstruct what each of these neurons has detected. And if the neurons are detecting patterns, I would expect that eventually I'm going to reconstruct something that looks much like the input, because each of the neurons has detected a key feature in the input. Now, this is not going to exactly reconstruct the entire input, because in this particular example, the first layer neurons are only looking for specific patterns that either distinctly identify digits or not. So it's going to reconstruct digit-like components of the input, but you get the idea. Every one of these neurons is looking for a very specific pattern. If that neuron fires, I can just reconstruct that input. And so using the combination of these neurons, I would have almost completely reconstructed the input. So let's formalize this. Let me, second. Now, in this case, it's not exactly going to reconstruct the input, because it's only going to retain distinctly digit-like or obviously not digit-like features. And the rest are going to be irrelevant because I trained the network to perform digit classification. But let's make this more simple. Let me say explicitly, I want the network, these neurons, to learn features such that when I put them back together, I reconstruct the input as exactly as possible. Now, that's something I can actually do. And how would I do this? This is what you call an autoencoder. You're going to try to train this network. Now observe something interesting here. If this neuron detects a horizontal line on top, you want to redraw the horizontal line on top, right? Which means that this weight going out is going to be the same as the weight going in, because you're reconstructing the same patterns that you saw in the input. So the output and input are basically the same weight matrix. One is a transpose of the other. And so I can explicitly try to train this model such that the output is as close to the input as possible. This is what we will call an autoencoder. Now, let's take the simplest autoencoder and see how it works. In the simplest autoencoder, I just have one neuron. And just to simplify matters further, I'm going to assume that that one neuron has a linear activation. There's no nonlinearity at all. So this one neuron is simply going to be outputting W times X. Then when I recompose it, then it's going to be W transpose times the output of this neuron, which is W times X. So if I'm going to be training this guy, then what I would be doing is minimizing the error between the reconstruction and the input, which is W transpose W times X and the X itself. So this is the simplest case of the autoencoder. It has only one neuron and it doesn't have a nonlinearity. Now, those of you who have actually been awake through all of your machine learning classes in this lecture know what this looks like. This is basically principal component analysis. So you're really finding, what you're really doing over here is, if you're trying to find the weights such that this error is minimized, what you're really finding is the one principal component that best characterizes the entirety of your data. So an autoencoder with just one neuron and no nonlinearity performs PCA and finds the first principal component. Now, basically, it finds the distance direction. If the data are zero variance, it finds the direction of maximum variance. More generally, it finds the direction of maximum energy, right? So now here's the thing. Regardless of the input, the output is going to be some scaling of W. Because as you can see, the output is simply W transpose times the output of this neuron, right? So regardless of what goes in here, some scalar comes out here. And so the actual reconstructed output is going to be a scaled version of the weight vector. So which means that regardless of what you put in, the output is always going to fall on this line. It's always going to learn a line, and it's always going to reconstruct data on the line. Now, and so here's where we are. If I just take the output portion of this network, regardless of what I give it as at the input, so regardless of what I feed as Z over here, the output is going to be something on this line. So it's a linear principal component analyzer. And so here, earlier I assumed that these two weights were the same. Even if they are not, it's going to say the behavior doesn't really change. A network of this kind is simply going to perform principal component analysis. Now, instead of having just one neuron, let me increase the number of neurons. Let me say there are some K neurons in the hidden layer. I'm still assuming that the neurons have linear activation. So if the neurons have linear activation, the optimization is still the same. I'm minimizing the error between the input X and W transpose WX, which is the output. And this is still principal component analysis. When you optimize it, it's going to find the principal subspace that explains the data most. And more important, so basically it's going to find the hyperplane such that if all the data were projected onto it, it captures most of the energy in the data. And the other interesting aspect of it is that if I consider just the output portion of this network, it's always going to reconstruct something on the hyperplane. So just some terminology. The portion of the network that computes this intermediate representation is generally called an encoder. The portion of the network that reconstructs the input from the intermediate representation is called the decoder. So that's why it's an autoencoder. The analysis is performed by the encoder, and the reconstruction or the synthesis is performed by the decoder, right? And so here's the thing. In this case, if you look at this network, if these things have linear activation, right, then the output is just going to be some weighted, some weight times the output of the final output of the network, the x hat, is simply going to be the weight times the output of the hidden layer. So that's just a linear combination of the hidden representations, which means that regardless of what goes in here, the output is always going to be on this hyperplane. So this performs principal component analysis, where the output weight matrix give you the bases of the principal subspace, and it's linear. But then let me do something over here. Let me get rid of this notion that I'm only going to be using linear activations for the hidden layer. So let's say I allow the hidden layer to also have a non-linear activation. Then what happens? And then, interestingly, the whole thing becomes non-linear. So the model no longer just finds the principal linear subspace. It actually finds the principal curved manifold that the data mostly lie on. And so this is the beautiful part of this entire structure. It actually performs non-linear principal component analysis. Anytime I have an autoencoder of this kind, it's actually performing non-linear principal component analysis. It's finding the principal manifold that the data mostly lie on. And so if this decoder portion gets more complex, has more layers, more non-linearities, it can reconstruct more complex, complicated manifolds, and it will capture the manifold that the data lie on with greater fidelity. So here is a very nice couple of very nice examples. In this example, all of my data lie on a spiral and with some noise. So if I were to ask you, what is the principal manifold of this data? Every one of you is going to tell me that it's a spiral. So here's the network that I used. This was it's an MLP. There's a hidden representation which is only one scalar. They have several layers, nonlinear layers going in and several nonlinear layers coming out. Now, if the network were properly learned, then you would expect that this hidden representation is going to find the position on the spiral, and that this output, the output portion of the network, is actually going to reconstruct the spiral. And indeed, that is what happens. You find that if you look at what this network learns, the decoder of this network learns to reconstruct the spiral. And so anytime you feed an input, it's projected to on some point on the spiral. Now, it's only going to learn the structure of the spiral within the region in which you have training data. If you try to extrapolate beyond it, you're going to get some rubbish. And even there, you're going to get the occasional, odd behavior. But the point is this: it actually learns the structure of the manifold that the data lie on, which is beautiful, right? So here's another example. These are data on a sinusoid. And once again, if I train this network with just one hidden representation, that the decoder learns the structure of the sinusoid, and the hidden representation gives you the position on the sinusoid. It actually learns to reconstruct data just on the sinusoid, and also learns to find out where on the sinusoid the data lie. So now this has a very beautiful interpretation. And the interpretation here is that the network, in the process of learning to analyze the data, learns the principal manifolds on which the data lie. So in fact, when you use this network to train a classifier, it first learns the principal manifold, then it straightens it out, moves things around, and then positions this such that the classes are linearly separable. In the autoencoder framework, basically the whole thing just performs nonlinear PCA, where the decoder learns the surface on which the data lie. So again, the key bit is that this decoder can only generate data on the manifold that the data lie on. So because, for example, in the PCA case, it can only generate data on the hyperplane. In the spiral case, the decoder can only generate data on the spiral. More generally, it's going to learn the manifold that the data lie on, and it can only generate data on that manifold. And this is something that you can put to good use. So this, you can actually make it a generator for that class of data. It's something, this is the behavior that we use in pretty much all of the generative models that we currently have, where we train the network to learn the manifold that the data lie on, so that random sampling from that manifold is most likely to give you data of the desired class. So, for example, if I were to train my autoencoder using digits data, then if I use the decoder, regardless of how I excite the input, the decoder is only going to be able to construct things that look like digits. So regardless of what I give the input, the decoder over here, once I've trained it, what it outputs may not be a digit, but it's going to be somewhat digit-like, right? Or in this example, I've trained an autoencoder on spectrograms of saxophones. And then once I trained it, I threw away the encoder. And if I've done this training just right, then the decoder can only generate saxophone-like sounds. Let's see if this is the case. So in this case, we just fed the network some random input over here. It only generates a saxophone or a different input. So these are not pure notes, but these are saxophone sounds. It only learns to generate saxophone sounds. Or here's another example. This is from a clarinet, right? It only learns to generate clarinet sounds. So the beauty of it is that it has actually learned. This is not a very complicated model. This is like 6 layers. It took about 15 minutes to train. And I had to have about half an hour of training data. But it learns the structure. Now you can imagine the power of a model of this kind, right? And since I don't want to bore you to death and spend too much time, I'm going to begin wrapping up with a very cute application, okay? Given a mixed sound from multiple sources, I want to separate out the sources. So, for example, I got a mixture of guitars and drums, and I want to separate the guitars from drums. Now, there are lots and lots of tools out there which can do it, but the basic principle is very simple, right? I can learn a dictionary of building blocks for each sound source. I can learn a dictionary of building blocks for guitars. So a dictionary of building blocks for guitars is basically some model where when I excite the model, the only thing it can produce is guitar-like sounds. It cannot produce anything other than guitar-like sounds. Similarly, I can learn a dictionary of sound sources, generative dictionary for my other source, say my drums. Now this is going to be a dictionary which, when I excite it, the only thing it can generate is drum-like sounds. And then when I get a mixed recording, which includes guitars and drums, I'm going to use both dictionaries. And then I'm going to ask myself, what is the best way of exciting the guitar dictionary and the drum dictionary so that when I sum their outputs, it sounds like this music that I've just heard. So if I can do that, then I can say, okay, the guitar portion is separated out and the drum portion is separated out because I added them to construct the sound. It's what in our good old days we used to call analysis by synthesis, right? So let's see if that works. How can I do this with my neural networks and autoencoders? Very simple, right? Here, we trained an autoencoder for the first source, where I take lots of guitar sounds. Actually, I didn't take very much in this example that I'm playing you, half an hour, right? And then I train an autoencoder. And if I train the autoencoder just right, then the decoder of the autoencoder can only generate guitar-like sounds. Similarly, I train an autoencoder on drums. And if I train it just right, the decoder can only generate drum-like sounds because everything it constructs is going to be on the drum manifold, right? And so then, when I get my mixed recording, I mean, I'm not interested in the encoder anymore. I'm only interested in the decoder. This decoder can only generate drum sounds. This decoder, the other decoder can only generate guitar sounds. So I'm going to try to figure out how to excite these two decoders, what the inputs must be, such that when I sum their outputs up, it sounds like the music that I just heard. Now, how can I figure out what the inputs must be? I can use backpropagation, standard, all the same tricks that we use to train neural networks. They can not only be used to train the parameters of the network, they can also, for a given output, we can also try to figure out what the optimal input must be to generate the same output. And so I can just use backpropagation to learn I1 and I2. And then once that's done, the output of the first decoder using I1 is maybe the first source. The output of the second decoder using I2 is maybe my second source. Not very complicated. Again, this is only meant to illustrate a specific point that the model actually learns the manifold of the data. And let's see if this works. So here's a I've got two instruments. And just to give you an idea of what I'm expected to get, it's this. The point is, I'm not doing anything particularly complicated, nothing like the fancy models you see today, right? But and this was the first one is not perfect, but so anyway, and you hear some imperfections because saxophones, violins, but anyway, you get the idea, right? So what we've spent a lot of time doing through this day is to figure out what networks are, what they can represent, what their restrictions are. When you learn these networks, what do they learn? How do they perform what they're supposed to perform? And eventually what the internal representations are. And we've seen some examples of trying to actually use these internal representations for other purposes. There's nothing profound that we've actually learned today. If you never attended today's lecture, it wouldn't have made any difference to your life. But I think that's true of most lectures. So, but hopefully you got some insights which make you look at neural networks slightly differently. So thank you, and I'll take questions. Okay, I can, if you ask me the question, I'll speak it out. Yeah. So I'm not clear what you mean by topological manifold analysis. Could you explain that? Yeah.
Elaborate about the last part a little bit more, because I'm very interested in know more about topological manifolds. Thank you.
So we actually have no way of knowing what this manifold really is. What we really, again, and this is subject to all the usual caveats and restrictions that we have when we are learning very large models. But the point is that in the process of the underlying model is that any data that you see is going to be lying close to some underlying manifold. And this is going to be true for any structured data. If it's not white noise, it's close to some lower dimensional manifold, linear or nonlinear. And so the hypothesis, which seems to be validated over here, is that when you train these models in a sufficient amount of data, it actually learns to generate this manifold, points on this manifold. And so when you look at things like variational autoencoders or diffusion models or all the other fancy models that people come up with these days, These are just more and more increasingly sophisticated ways of learning this manifold in such a way that any residual noise is statistically independent of the data that lie on the manifold. Any other questions? Yeah.
One question. So whenever we look at different networks that try to learn the same sort of inputs, can we characterize their weight matrices in the same way? Imagine we learn a very big model, but then we want to distill that into a smaller one. Can we have like ways of understanding or even initialize the weights from the weights of a bigger model, let's say?
It's unfortunate that it's not really possible because, a simple thing like a rotation can throw you off. So, you can rotate, scale, unrotate, and unscale. And different components of the model can, undo various transforms that happen within it. And so it kind of defies very simple comparison across models simply because there are so many, even in the, ideal case, there are so many invertible transforms that can be part of your learning process that you don't know where you stay.
Right, so there's no way you can't, let's say, we know the dimension of the smaller size, let's initialize them to the first, I don't know, set of eigenvalues. Would those be?
So that's, yeah, again, if you initialize it to the first set of eigenvalues, you're assuming linearity of the manifold, right?
Okay.
And so you're going to be subject to those.
I see.
So it's hard. All of these have been actually tried and attempted, and what we eventually find is that you can come up if you look for a specific result, you will find it, and if you're not looking for it, you won't.
Okay.
Yes.
So how does it work when you are in space which has not a metric, which is not a differentiable variety?
So here pretty much we're assuming that all of this is a different. These are differentiables. If you're working on non-differentiable varieties, I don't think any of this math directly holds. Even our optimization is going to be broken, right? So we're going to need a different way of dealing with it. Yes. That's actually a common problem, and there's there's a class of modeling approaches which actually try to think of it in terms of non-differentiable mathematics, but eventually we approximate it as something differentiable simply because otherwise you can't track, it's not tractable.
But that's especially important for concepts
Yeah.
because we tend to think that concepts are geometry.
Yeah.
Might be geometry implies concepts, but
Yes,
there are some concepts which are not geometry.
absolutely, you're right.
What are the many advantages of using autoencoders respect to use linear or nonlinear PCA, for example?
The autoencoder is performing nonlinear PCA, right? So anytime you're performing nonlinear PCA, how are you actually going to be optimizing it? You're going to use gradient descent. The neural network is just, you can think of it as a function which is composed of simple units. That's about it. You can get rid of the entire, business of simple compositions of simple units, and the general principles still hold. So nothing changes. It's just about how you compose the functions. It's still nonlinear PCA. You can do it in other ways. There are various other models, all the classical machine learning models where we used to work very hard to come up with optimization algorithms where we're finding out that you can just use back propagation and the whole thing becomes tractable.
Thank you.
All right. Thank you, everybody.